start in a second. There's couple of ideas, couple of things, a couple of new applications, possible applications, couple of ideas from the robot. Actually had a couple of good ideas, but if you have some better ones, do let me know. Is it 100%? Yeah, it's 100%. So we have already mentioned this, that we have this new navigation tool. So it's on every page. It is on every page. I won't be able to turn this one on, would I? Because I'm using the camera for the stream. We actually had another camera in use. Yeah, so it won't even open the page. There's a video of me using it. Yeah, and you can see that the navigation menu is on every page. When you scroll up, it appears. When you scroll down, it disappears, which is a bit weird on a touchscreen. Have to optimize everything for a touchscreen, because even things like the live simulation wouldn't work on touchscreen. It just behaves very funny. So we have to make it better. There's shortcuts as well for the different elements, so they won't work, but that's kind of to be expected. Trying to generate like an incubator like this that will keep generating live. If you haven't checked it out, go check out this simulation. Let me know what you think, and also let me know if you are able, with as little water as possible, generate as much life as possible. So we want to save water, increase life, and this one's not kickstarting. The life is pretty dormant at the moment, so you can try creating another one of those incubators nearby. Create a tiny wall there. Yeah, it's kind of going. Yeah, I didn't do anything with that. Yeah, it started going by itself, all by itself. That's kind of nice. This live shortcut is 5. You can put drop the drop there, so drop the drop. Sorry for the pun. It's actually gonna generate something. I don't know if you can design your own incubator. That might be better than one we have. Can come back to it later, see how it went. Open another tab. I don't know how many resources the live takes. Could be in theory quite a few, but not as much as other applications. So more recently we had this so we have this section on medical imaging and data manipulation. We have this 3D brain where the images loading quite well. You can scroll through them with the mouse wheel. I think there's shortcuts as well. Yeah, they are up and down, but then when you press down, it's also scrolling down the page. So that's kind of not ideal. Not sure how to fix it. This page up, page down. Yeah, so left yeah, left and right. We'll move through the slices. The thing about it, it's still, it also has, yeah, house navigation. Yeah, we were measuring performance of this tool. It wasn't great at all. Yeah, so it takes about 100 seconds for this volumetric data to load as well. So let me know if you know of any way to improve loading of this thing. Yeah, I was saying in the previous stream, the original file is a nifty file, a very small one, only 32 megabytes. But then it's already loaded 129 megabytes into the browser alone. Yeah, go check it out. It's still running. You'll probably be overloading my server if you use it, or multiple users use it. Yeah, I have to actually check if Cloudflare, if the CDN actually can cache. I'm pretty sure it will be able to cache the images. It probably won't be able to cache the volumetric data as a JSON file. Actually, now that I'm thinking about it, it's probably that could be the reason why it takes so long to load. So go check it out. It's all free. Well, you'll be paying for some electricity when using the site. So that's not free. I also don't know why when you minimize the screen, it only minimizing these two panels, but not the main one. Obviously, seem to be trying to keep the volumetric data panel the same size. Also, another issue, obviously, that the rendering of the volumetric data is not great. I don't know what's up with that. Meant to look more like a 3D model of the brain of this specific scan. So I don't know how to, if anyone knows how to make it better, do let me know. What did we talk about last time? What didn't we cover yet? We have this a bunch of so this is exploring optical illusions, and yeah, this blog has a Python code that can actually generate these images. In this case, it's also you can control the position of that second line and actually see, you know, as you move it across, that's actually the same size. I know it might look longer because of that background image. So there's a description of what each optical illusion is, and the Python code for regenerating it. So it might be, let me know if you are interested in this kind of stuff. We're more than happy to do more on this. It's quite interesting. What else we got that we haven't covered prior? Yeah, I can't use any of those. I can't actually do a demo of any of the tools that require a web camera. Don't know why. The microphone would actually work because we had this. Yes, speech analysis. I think this one actually might work. So it says start speaking. The transcript will appear here. It does the volume, live, and the speech rate. Yeah, and in this particular model, you actually have to pause talking for the text, for the transcription to actually work. Yeah, it's an open source JavaScript tool, so check it out as well. Yeah, someone was complaining it's not working on the browser. I think it's only working on Chromium based. There's a description at the bottom with all the restrictions, disclaimers, and the like. Yeah, so this window will keep expanding as you talk. It's actually performing pretty well. Yeah, because I know if it didn't transcribe my speech properly, that's probably because I'm not talking clearly enough. So you can actually use it to practice your speaking skills. But then you might sound a bit robotic. Yeah, for it to properly work. Yeah, once you start talking quickly and normally, then it starts making more mistakes. Just go quickly over some of the other tools. I think I covered that one just recently. Yeah, we definitely covered the CardioBot. There are two versions of it. Yes, they're not really duplicated. The CardioBot is more advanced. The CardioQuest is more basic. Yeah, this one will work. This one just teaches you about the hits, false alarm, correct rejections, and misses. You can find abnormal ECG patterns, avoid clicking on normal ECG, so you gain points, and it will do the, what's the table called? Yeah, there's hundreds of different ways of calling this stuff. We could actually, now that I'm thinking, yeah, that's a normal one, so I'm not clicking on it. Once it's passed, I'm getting 10 points as well. This one is abnormal. And then if I miss an abnormal one, misses go up. This should happen again because I didn't click on it. If I do click on it, it's a hit. Every 50 points, the speed goes up as well. And a false alarm is when we have a normal one and I actually click on it. So that was a false detection. So my false alarm count went up. And yes, there is a, when it goes below 50, it will go slower again, giving you, longer window of opportunity to get it right. I think the rate between normal and abnormal is actually 60-40. So you could just by not clicking gain some points maybe, or maybe it's 60-40 the other way around, so 60% abnormal that you do have to click on. Yeah, that makes more sense. So then the number of points will gradually go down if you don't actually interact with the application. Now that I'm thinking about it, we could actually add a rock curve to it, modified on the fly. That would actually be quite good, wouldn't it? So we can have another version of it. We do have another version where we apply fuzzy logic analysis. So this one is essentially the same thing but more advanced. It has you can reduce noise level and see how essentially an explainable AI algorithm performs. it's a fuzzy logic algorithm. You can see what it's doing at the bottom here. So it's essentially looking at the number of positive peaks. So you can see when the noise is increased, it's giving you 35, and it's really sending the algorithm into la la land, and it cannot perform. The performance is, so it's giving you abnormality score, and the performance is being calculated. So the machine is still doing quite well, even with increased noise. Well, it did do false detection, so it's essentially more likely to say the waveform is not normal. Every time I say abnormal, the speech to text, the transcriber, even Google ones that meant to be really good, is stuffing the text up. Yeah, if you reduce the noise, then those false alarms should go away. It's actually that slow at the moment because the human score is -50, so it's giving a human a better chance to actually start performing again. Yeah, the main advantage of the machine is that it can make a decision in fractions of a nanosecond speed, whereas a human takes more time. So saying before, we might have, just build upon this and have a third version that also has a rock curve being plotted as you play the game. How hard would that be, you reckon? Yeah, we probably should go from the simpler version of it. Yeah, obviously that will be better. So essentially the idea is that you will have a rock curve chart on the side of the screen. Yeah, by the way, there was a problem with this thing. In terms of the display would not scale properly on different screen sizes, which was a bit annoying. Do we get errors as well? What? A console. Ah, no, it's fine. It's not my errors, it's Google. I'm saying we have a version of this that will also show a rock, a curve. Can you explain a rock curve in plain text without any code? Continuous sentences, full paragraphs. No emojis, no dot points. It's actually rock curve, just ROC. Check how life is going. Oh, it's still going. I mean, it's going because of the pool of water at the bottom of the screen, but the incubators we made, are they gonna kickstart generating life? Maybe. We'll come back to them. Yeah, so the bot in this case doing pretty well. The human score is going down, the machine is winning. Well, mainly because I wasn't paying attention. You can make it harder for the machine by increasing the noise level. So then the machine score in theory should start going down as well. So it will make more false detections and misses. In this one is a simpler version of the same thing where we only have the human interaction. No robot is doing the same task at the same time. And we were asking about rock curves. There's a general description. It's like Wikipedia style stuff. Shall we read it anyway? Let's do it. Well, actually, can you make it more fun and give examples from a biomedical signal detection? For example, ECG. You could use EEG as well if you like, and make it fun. What did it updated uh, memory for? It says it prefers more engaging and fun explanation. Well, obviously, particularly when explaining concepts using examples from biomedical signal detection, such as ECG and EEG. Okay, that's fair enough. Best friend. That's a bit lame. Okay. I mean, yeah, I'm pretty sure there's nothing wrong with it. Let's actually read it out loud so I don't lose my voice by the end of this.
Imagine you are a biomedical engineer trying to design a system that can automatically detect certain heart conditions from an ECG, like atrial fibrillation. Your goal is to build a classifier that can tell, based on an ECG signal, whether a patient is experiencing this condition. However, as with any diagnostic tool, your system is not perfect, and sometimes it might make mistakes. Now, let's say you're tuning your system to make these decisions, and you have to choose a threshold, a point at which the system decides, yes, this person has atrial fibrillation, or no, they do not. If your threshold is too low, your system might start freaking out every time it detects even the slightest irregularity, sending out false alarms like there's no tomorrow. On the other hand, if your threshold is too high, it might miss the real warning signs, letting a serious condition slip through unnoticed. This is where the rock curve comes in. Think of it as a tool to help you find the sweet spot for your system's decision making. It's like setting up an ECG dance off where your classifier is showing off its moves. On the dance floor, you have two important metrics: the true positive rate the number of times your system correctly identifies atrial fibrillation, and the false positive rate, how often your system mistakenly cries wolf when everything is fine. As you slide that threshold up and down, your system's dance moves change. Sometimes it's more accurate, sometimes it stumbles. The rock curve captures all these moves, plotting the true positive rate against the false positive rate at each possible threshold. If your classifier has great moves, it will get up close to the top left corner of the dance floor, where it's nailing those true positives while keeping false positives to a minimum. For example, imagine you're testing your system on a bunch of ECG signals. If your rock curve is a smooth, graceful line that arcs toward the top left, your system is a superstar. It's doing a great job of catching atrial fibrillation while not making too many mistakes. But if your Arak C curve is more like a lazy shuffle toward the diagonal, your system is just guessing, barely doing better than flipping a coin. Now let's mix in some EEG fun. Suppose you're building a system to detect epileptic seizures from EEG signals. The stakes are high, just like with the ECG example, and you need your system to be both sensitive and specific. The Rock C curve comes to the rescue again, helping you tune the system so that it's super sharp at catching those seizures while avoiding false alarms that could cause unnecessary panic. The area under the Rock C curve, or AUC, is like the final score in this dance-off. An AUC of 1.0 means your system is a dance prodigy, flawlessly detecting the condition every time. An AUC closer to zero point 0.5, though, suggests your system is still learning the steps, not yet ready for prime time. In short, the Arak C curve is your best friend when you're trying to get your biomedical signal detection system to perform at its best. It helps you strike the right balance between catching real health issues and avoiding unnecessary scares, whether you're working with ECG, EEG, or any other biomedical signals.
Yeah, that's not bad explanation. I mean, it's definitely better than I would ever come up with myself. Now the question is, so what if we just give it an image? Oops. Let's give out. Did it get it? Sorry, I was pounding the keyboard. It wasn't intentional. Okay, maybe we'll give it a couple. And this should be a good one. Yeah, so the question is, we want to add a rock curve. We'll probably be turning it into another web application, but let's, okay, I pressed the wrong button by mistake. That's fine. Clear. Clear does work because I'm using a different, actually using a different text to speech. Yeah, let's just send it as is, see what it comes up with.
It looks like you've shared screenshots from a game called Cardio Quest, where you identify abnormal ECG patterns. In this game, you score points by correctly identifying these patterns, hits, and avoiding normal ones, correct rejections. However, if you mistakenly click on a normal ECG pattern, it's a false alarm, and if you miss an abnormal one, it's counted as a miss. This game is a perfect example to connect with the rock curve concept. Each time you decide whether to click on an ECG pattern, you're essentially setting a threshold for what you consider an abnormal pattern. Your hits, true positives, and misses, false negatives, reflect how sensitive you are to detecting abnormalities. Meanwhile, your false alarms, false positives, and correct rejections, true negatives, show how specific you are about not tagging normal patterns as abnormal. If you get too cautious and only click on the most obvious abnormalities, you'll miss some true abnormalities, increasing your miss count, but keeping false alarms low. On the other hand, if you start clicking on anything that looks remotely abnormal, you'll catch more true abnormalities, hits, but you'll also mistakenly tag normal ECGs as abnormal, increasing your false alarms. Your performance in the game could be plotted on an ROX curve, showing the trade-off between the true positive rate, hits, and the false positive rate, false alarms. A well-balanced strategy would create a curve that bows towards the top left, indicating that you're good at catching true abnormalities while avoiding false alarms. If your curve is more diagonal, it might suggest you're either guessing or have a poor balance between sensitivity and specificity. In essence, the game is teaching you to find the right threshold, a balance between being cautious enough not to miss true abnormalities and being bold enough not to mistake normal patterns for problems. The better you get at this, the closer you'll get to mastering the art of diagnostic precision, both in the game and potentially in real-world scenarios.
Yeah. Okay, I wasn't really listening, but it sounds it sounds really good. Um, let's we actually start another Flask application. Yeah, we'll get the robot to do it all, but we should have a template. So we have a bunch of them. So these two, we have CardioQuest and CardioBot. So the CardioQuest should be a more simple one, because it's also one where we have the waveforms being generated. That stuff we want to reduce. Yeah, CardioBot, CardioQuest. Yeah, we're using CardioQuest. Yeah, we have this waveforms JS, so they're being generated by Python as well. We might actually make them different or better, potentially add more. I don't know yet. For now, just keep them as they are. Other two. Yeah, it's not organized in a great way, is it? I have to reorganize it into a Flask application. Just JavaScript at the moment. We actually don't want to do much on the server. Yeah, later if we want an option to add like a leaderboard or things like that. So just going for the simple version of it. Simple version. Simple version. Let me think. By the way, this session is meant to be interactive. So yes, I'm doing a lot of live streaming. If someone wants to join in, even develop together or go live, can go, all the options are open. Can go voice only, voice and video. You can just check the website, provide your feedback. You can, yeah, you can do what you want, really, but this is all open source stuff. Let me just also check if we. So we want to add things like currently we have, yeah, ethics, brain, EEG, cardio, ECG. It's most of the tools are around the brain waves and EEG. But yeah, some cardio stuff, simulations and games. There's some vision stuff, cochlear implants. So I did my PhD on cochlear implants. I should know a thing or two about it. Probably should do some more hearing related stuff. what the other ideas were, they were quite, it's actually quite like a bunch. Yeah, ultrasound data, visual acuity data, because that one is actually using your own eyes, but it's not collecting any data unless you did like a video of it or something. Which actually someone did like a video with the eye tracker. Yeah, obviously when you record a video, you generate a lot of data. And if you post it as well, you can actually share that data. So that's great. Yeah, I might have a blog on just covering a list of going over publications that actually have data in them. So I'm just, yeah, showing publications is a bit of a problem because it's copyrighted material. But we always looking for open source data science around biomedical data publications, but that actually published the data. So yeah, don't read any papers that haven't published the data because you can't reproduce the results. There's essentially, yeah, no point. No point. Yeah, so we need a Flask application. Have a waveform generation. Just go with the board. Did we read this already? Yeah. If I start telling it's a Flask application, it will start generating code. Yeah, can we? So without generating any code, without including any code in your response, can we just in plain text, continuous sentences, go over of how we could make a Flask application? We already have a bunch of them on deployed on our Apache server. But yeah, so we have all we know how to deploy, so that's fine. We know how to set up a Flask application. That should be okay. For this particular tool, yeah, if you could generate an idea of how we should go about designing one from scratch or not, I don't know. We have two similar tools already deployed. There is a waveform generation code in JavaScript. So we have samples already available. I can share the code with you if necessary. Or shall we design this from scratch? What else? We want to optimize it. The previous versions were not optimized for mobile. So the screen didn't scale properly. We would like to have something that works on a mobile screen as well. So we're generating data in this application by clicking on the screen on when a not normal ECG waveform is scrolling past. When it is normal, the idea is, yeah, so you know what's the deal, you can explain it yourself. But yeah, just go for text alone at the moment, and we will start generating code in future prompt responses. Should have done like a single shot prompts work much better. Was it updating memory? It's like, it's funny how it's essentially like telling you, I'll remember this about you. Has previous experience deploying Flask application. Yeah, that's right. On the Apache server, knows how to set up a Flask application. They want to design a new Flask application from scratch, optimized for mobile screens, and have waveform generated. Yeah, so those are details that are specific for this application. I hope, when we do future chats, they are not actually affecting the responses. Let's read this quickly.
Given that you already have experience with deploying Flask applications and have a working setup on your Apache server, we can dive straight into the conceptual design of the new application. The goal is to build an optimized mobile-friendly application where users can interact with ECG waveforms by clicking on abnormal patterns as they scroll past the screen. Here's how we can approach this. First, let's think about the user experience. Since the previous versions weren't optimized for mobile, one of the key aspects of this new design will be ensuring that the application is fully responsive. We'll want to use a responsive front-end framework like Bootstrap, or consider building a custom CSS solution that ensures the application scales well across different screen sizes. The main interface will need to adapt to both desktop and mobile users, ensuring that the ECG waveforms are easily viewable and clickable on any device. The core functionality revolves around displaying ECG waveforms and allowing the user to interact with them. Since you already have waveform generation code in JavaScript, we can integrate this with the Flask backend. The Flask application will serve the front end, handle user inputs, and possibly store interaction data for later analysis. On the back end, Flask will handle routing, serving the main game page where the ECG waveforms are displayed. We might consider setting up endpoints that the front end can call asynchronously to fetch new waveform data or send user interactions, like clicks on abnormal segments. This asynchronous communication will allow the application to remain responsive without requiring full page reloads, enhancing the user experience, especially on mobile devices. For the data handling, since the primary interaction involves users clicking on abnormal ECG waveforms, we'll need a way to capture these events. The backend will likely need to record each click event, storing details like the time of the click, whether it was on a normal or abnormal waveform, and the user's score at that moment. This data could be stored in a simple SQLite database or sent to an external storage solution, depending on your needs. To enhance the mobile experience, we should consider touch-based interactions and gestures. On mobile devices, the interface should be optimized for touch inputs with larger, easily tappable areas to ensure that users can accurately interact with the waveforms. The display of the waveforms themselves might need to be adjusted for smaller screens, perhaps by slightly simplifying the visuals or allowing users to zoom in on the waveforms for more precise clicks. In summary, the design will focus on creating a responsive, user-friendly interface that integrates your existing JavaScript waveform generation code with Flask's backend logic. The primary interaction will involve users clicking on scrolling ECG waveforms, with Flask handling data capture and possibly some game logic, such as updating scores or providing feedback to the user. We'll aim to ensure that the application works seamlessly across devices, with particular attention paid to optimizing the experience on mobile screens.
Yeah, that sounds great. Do you need the bit that generates the waveforms, or shall we just continue with the concept? and fill in all the details, all the technical stuff later. How about we do the overall structure, so files and folders for this web application? If you can include the WSGI file as well, that would be great. We also want to do as much as possible in JavaScript, so the end user is paying for most of the electricity, and only use backend if absolutely necessary. Now we also using Cloudflare's CDN, so if possible we wanna cache as much of the data as possible. I wonder if it will understand that cache is not cache, but let's see. If it starts generating code, we'll probably revert back to text only. Apparently github.com is down. Can you compare? Can you compare GitHub to YouTube? It's still generating, or what is it doing? Do I need to select a different model, or it's actually gonna generate something?
Given your preference to handle most of the computation on the client side using JavaScript and leverage Cloudflare's CDN for caching, we can outline the overall structure of your Flask application, including the necessary files and folders. This structure will ensure that your application is well organized, scalable, and optimized for both performance and maintainability. Overall project structure. Here's a suggested structure for your Flask application / your Flask core app. CSS, styles.css, JS, main.js, waveform.js, images / templates, index.html, cache.htaccess, /instance config.py /logs error.log tests test waveform generation.py test app.py config.py wsgi.py requirements.txt. Mash breakdown of the structure. This directory will contain all your static assets. Your CSS files for styling the application. JS, JavaScript files where main.js handles the general functionality of the application, and waveform.js is specifically for generating and managing ECG waveforms. / images, fonts. Directories to hold any images or fonts used in the application. This templates. This folder will store your HTML files. The index.html file will be your main page where the user interacts with the ECG waveforms. Cache. This directory will manage cached content, particularly to take advantage of Cloudflare's CDN. You might use an .taxs file here to control cache behavior at a granular level. The instance folder will hold configuration files that are not checked into version control, e.g., credentials, secret keys. The config.py file can hold environment-specific settings. Logs. This directory will store your application's logs. The error.log file will capture any issues that occur during runtime. Tests. Your test files will go here. It's a good idea to test both the backend logic, like endpoint functionality, and the JavaScript code, like waveform generation. App.py. This is the main entry point for your Flask application. It will define routes, handle requests, and serve the necessary HTML and static files. Config.py. This file will hold the global configuration for your Flask application, such as debugging settings, database connections, if needed, and other configuration options. This is the WSGI entry point to your application, used by your Apache server to serve the Flask app. This file typically looks like this. Python from app, import app as application, if name equal with score main, application requirements.txt. List all your Python dependencies here. It ensures that anyone setting up your project has the correct libraries installed. Key considerations for optimization. 1. JavaScript-heavy processing. By doing most of the waveform generation and interaction handling in waveform.js, you ensure that the client's browser does the heavy lifting. This will reduce the load on your server and enhance scalability. You can use modern JavaScript features like web workers to handle any intensive computation in the background, keeping the UI responsive. Number 2. Caching strategy. Utilize Cloudflare's caching as much as possible. Your static assets, CSS, JavaScript images, should be set to have a long cache expiration time, as they don't change often. The /cache directory can be configured to manage dynamic content that benefits from caching. 3. Responsive design. Ensure that your CSS in styles.css uses media queries to adapt the layout for different screen sizes. This ensures that the application works seamlessly across devices, especially on mobile. 4. Asynchronous communication. If the backend needs to be involved, e.g. for storing user interactions, use Ajax or Fetch API in main.js to communicate with Flask asynchronously. This keeps the user experience smooth without full-page reloads. This structure should provide a solid foundation for your new Flask application, optimized for both desktop and mobile use while leveraging client-side processing and effective caching strategies.
Well, first, I forgot about, I asked it to add the request. Where is it? The WSGI file. So it forgot to do that. A couple of things. We forgot to add the WSGI files. WSGI. Yeah, that's right. Also, can you specify which files are not absolutely necessary? And also, can you give suggestions, say 5 suggestions for a name of this application? Yeah, like, yeah, a lot of this is optional, isn't it? So we have WSGI in it as well. That's not optional, we actually need it. Where is it? No, wait, it's not WSGI pi. It's yeah, we need CSS, we need JavaScript. Away from JavaScript, we actually have it from the previous project, so we might reuse it. A central Flask application necessary for deploying application Apache server. Yeah, that's actually called something else. It's actually called something else. Wave. Okay. Wave Watch. Wave Watch. It's a code name. CG Quest. We already have something similar. Cardio Click. Pretty good. They're pretty good names. Cardio. No, this should be something. The rock curve. The name should include rock curve in it. But the first one, the first two are pretty good. Now, also the WSGI file is not a Python file, it's a settings file. It's actually a dot. It's actually called, say, my app dot WSGI. I don't know if this file is necessary, but I have it in every Flask application. Maybe you can comment on that and suggest more names. Yeah, the ones they did so far pretty good.
Clarification on the .wsg file. The .usg file is indeed necessary when deploying a Flask application on a WSGI server, like Apache or Nginx, with UWSGI or Gunicorn. This file acts as an entry point for the WSGI server to interface with your Flask application. Typically, this file is named after your application, e.g. myapp.usg, and is not a Python file, but a configuration file that instructs the server on how to run your Flask app. Here's an example structure of a .wsgi file. Python import sys import os. Hack path to your application. sys.path.insert 0 /path to your Flask app. From app, import app as application. This brings in your Flask application. Optional, you might need to set environment variables or paths here. This file is important because it tells the server where to find your Flask application and how to execute it. It's definitely recommended to keep this file in every Flask project you deploy to ensure proper server communication. Updated name suggestions, including rock curve. 1. WaveWatch Rock, a combination that ties the monitoring aspect with rock curve analysis. 2. Cardio Rock Quest, integrates the idea of a quest or challenge with Rossi curve detection. 3. Rock Curve Click, emphasizes the interaction aspect while directly referencing the rock curve. 4. Rock Pulse Detect, combines the idea of pulse
Cardio Rock is
detection
pretty
with
good.
the rock curve concept.
So let's
5.
start another
Rhythm
web
Rock
application
Seeker,
that
a
calls
name
that.
that suggests searching for rhythm irregularities using rock curves. These names aim to
By the way, when
balance
I'm
your initial
recording these
preferences with the
videos, I
requirement to
should
include
test
rock
it,
curve,
but
ensuring they remain
two
catchy and
voices,
relevant to your application's
two
purpose.
sound channels from my computer and the microphone should go into separate streams. So when I actually edit the videos later, I'll just get rid of the robot, but you can still, watch it live, live interacting with it. Just keep it if absolutely necessary, if I'm actually responding to whatever it said. Yeah, I wish you could actually talk to it like a person. Might have another one. What if I have, would I run into limits or something if I just have another one on my phone? Would that work? I know what the problem would be. Problem would be it will be talking over me. I can try it out. I don't just use the. Let's see later how it works. But I wanted to hear this robot as well. Yeah, ideally, of course, it will all go into the stream. Can go into the stream. The Cardio Rock name is pretty good though. Cardio Rock. How do we quickly on a different topic, a quick response in a Visual Studio Code? How do we change the order of files in the file and folder explorer from by date to alphabetical or order? I don't know, why do you need tutorials anymore? We can just ask the bot. Let's see if it's actually open command palette. A Control Shift P. Sort files. No, it's a bit wrong. That's a bit wrong. I need to search for commands. Control Shift B. Can't find it. Explorer. Sort. That's the problem when you have like a gazillion of options in the IDE. Like, how do you? They can regenerate. Why the older model sometimes gives better results. Just testing how these models work or do not work. Visual Studio Code, blah blah blah. Okay. No. Why do I need to install? No, I'm pretty sure I did this before. Oops. I recently used commands, but Explorer. Confirm, delete. Okay, come on. File sort order. Right. Did find it. The GPT-4 didn't really help with this. Okay, so we have cardio. Yeah, cardio rock. We definitely need my app. Let's regenerate the file and folder structure. WSGI to replace it with a name. I mean, my app used to work before, so that should be okay. It's actually making a suggestion there. We also have an info. Info text will have the structure. Okay, it's called cardio rock. Actually might open it in a separate window. And this is tricky because there's a chance that Visual Studio Code will crash on us. But we'll try it anyway. Yep, cardio rock it is. We have the structure for it. There's a lot of optional files. WSGI made a suggestion. Okay, this is what we have for the my app WSGI file. We actually took it from a different project that works. Now also, can you generate a terminal script that will generate all the necessary files and the subfolders? We are already in the project folder. Yeah, we're already in this folder. What? Uh, why can't we just copy paste it? Hey, why can't we just copy paste it? Can you just start? Let's just do step by step. We will just generate the files and folders first, and then populate the code within each file in the future. Okay, this is better. So all the folders. We have cache, instance, yes, CSS folder, fonts, probably don't need fonts. Have a lot of optional stuff. Okay, there's the app. As we, where is it? Test. Yes, starts as a JavaScript. Okay, we have a waveform JavaScript from another project. From another project. Kali Quest. Yeah, we have this waveform JS. So we have this waveforms JS from another project. They just work. Can we use them here as well, or would you suggest changing or improving it somehow? Yeah, we have it working in the cardio bot business. It's working fine. By the way, as a side note, I'm not sure why with very high noise level the machine is still being able to perform and increase performance. Well, I think I know why. It's because it's just pounding on a abnormal, so it's just deciding that everything is not normal ECG waveforms, and because the ratio is 60-30, 60-40 for not normal and normal, therefore the score keeps overall going up. That's to be expected, I guess. So we have this waveforms generated. Yeah, let's read that quickly before I lose my voice.
The waveform.js code you've shared is quite well structured and functional for generating different types of ECG waveforms, including variations that simulate abnormal conditions. You can certainly use this code in your new Flask application without significant changes. However, here are a few suggestions for potential improvements or considerations, depending on your specific needs and goals. Harbor 1. Refactor for readability and maintainability. The current code is well organized, but you might consider breaking down some of the logic into smaller functions for better readability and easier maintenance. For example, the generate full waveform function and its variations could be broken down into even smaller functions, like handling P-wave, QRS complex, S-wave, and T-wave separately. 2. Enhance performance. If the waveform generation becomes a performance bottleneck, consider pre-computing some of these waveforms and storing them as JSON files. This way, you could load the waveform data from files instead of generating them in real time, reducing the computational load on the client side. Hatter 3. Improve scalability. Currently, the code handles a set number of waveform variations. If you plan to add more variations or different types of abnormalities in the future, you might consider creating a more modular system that makes it easier to add new types of waveforms. 4. Optimize for mobile. Since your application needs to be optimized for mobile screens, ensure that the JavaScript handles rendering well on smaller devices. This might involve adjusting the canvas size dynamically or ensuring the waveforms are displayed clearly on different screen sizes. Har 5. Consider integration with Canvas or SVG. If you're planning to render these waveforms visually in the browser, you might want to integrate this JavaScript with a Canvas or SVG element to display the waveforms smoothly. This integration could be straightforward or more sophisticated, depending on how interactive you want the visual display to be. Implementation plan. Given these considerations, you can start by integrating this waveform.js code directly into your new application and test its performance and visual output. If everything runs smoothly and meets your needs, then you might not need to make any changes. If you encounter performance issues, or if you want to expand the functionality later on, you could explore the suggestions above. Let me know if you'd like to proceed with this approach, and I can assist you with integrating the waveform generation into your Flask application, or making any specific improvements you choose.
Okay, so we can just continue with the waveform generating JavaScript as it is, like integrating it into the Flask application, and then improve it later if necessary, or change it later if necessary. Okay, so we are referencing it in index.html. I think we can actually test the HTML yet, can we? Are you suggesting just running the HTML by itself or through the Flask application? Because currently we don't have anything in the app by file. Expected. Move the HTML to test location. Yeah, we just go for setting up the Flask. No, that's okay. We'll just go for setting up the Flask. Yeah, we should have the structure. That's okay. Can run the Flask app No, that's okay. The Flask app did run without any issues. But yeah, well, should know how to continue, right? No, I mean it's running okay, but it's not actually displaying anything. Displaying anything. Displaying. Display. I can't get mine. Yeah, obviously. Need to change stuff in the HTML. Yep, waveform canvas will be nice. JavaScript main, yeah, we should have those folders. Yeah, I'm pretty sure it's rendering correctly. Now I'm pretty sure it's rendering correctly, but there is nothing in the main JS file at the moment. Can we address that? Cardio Rock is a good name. Okay, wait a sec. So if we're setting up the canvas width and height to be fixed, how would it work on a mobile device or when the window becomes much smaller? Great, great observation. Yeah, just keep it as canvas. Yep, that sounds good. It actually knows what we want. So it goes into JavaScript, main.js. Okay. We have the waveform. Yeah, when we hit the F5, it's generating a new waveform. Yes, some of them don't actually fit the screen. That's the normal one. They should be inverted, aren't they? They should be inverted. Yeah, it looks like the waveforms are upside down, but the good news is that they are actually displaying. When I hit F5, it generating a random one, but they are currently displayed upside down. Can we address that? Yeah, that's the essentially if you keep refreshing the page, you can see you can scroll essentially through all the waveforms that we have. There's not many of them. Let's read that quickly.
Great to hear that the waveforms are displaying. If the waveforms are appearing upside down, this is likely due to the way the y-axis coordinates are handled in the canvas. In a canvas, the origin 0, 0 is at the top left corner, with y values increasing as you move downward, which can cause things to appear inverted when drawn. To fix this, we can flip the y-axis when drawing the waveforms. Here's how you can adjust the drawing code, updated main.js. We'll modify the drawing function to invert the y-axis by subtracting the waveform value from the canvas height. JavaScript document add event listener, DOM content loaded function, const.
Okay, that's fine. It's working okay. It's now displaying the right way. So that's great. As you can see from the image though, it doesn't always fit, especially the tip of the R peak is chopped off. It's not visible. Can we address that somehow? See, we're not reading through the code. There is no way, but we will read the intro to see if it's understood what the problem is.
It looks like the R wave, which is the tallest part of the ECG waveform, is getting cut off at the top of the canvas. This typically happens when the waveform values exceed the canvas height. To address this, we can apply some scaling to the waveform values to ensure they fit within the canvas dimensions, even at the highest peaks. Here's how you can modify the draw waveform function to scale the waveform correctly. Updated main.js JavaScript document.add event listener DOM content loaded function const canvas equals document.get element by ID waveform canvas const ctx equals canvas.get context 2D function to resize the canvas based on the window size function resize.
Okay, this is better. So it is scaling whatever, but I don't particularly like the scaling. Perhaps we could just shift it down a bit, just so the R peak fits in, but then we want the baseline always to be at the same position. Let's see if it can do it without an image. Yeah, so just stretching it essentially. Don't particularly like it. It's okay in terms of fitting in, but let's see if it understood what the problem is.
If you'd like to avoid scaling, but still ensure that the R peak fits within the canvas while keeping the baseline in a consistent position, we can achieve this by shifting the waveform down slightly. This way, we can keep the baseline at a fixed position near the center of the canvas while ensuring that the tallest peaks, like the R wave, don't get cut off. Attached updated main.js. Here's how you can adjust the drawing logic to shift the waveform down without altering the scaling. JavaScript document.add event listener DOM content loaded function const canvas equals document.element by ID waveform canvas const ctx equals canvas.get context 2D function to resize the canvas based on the window.
Okay, this is much better. I didn't say Google. Okay, this is much better. Can we move on? Yeah, there is a timing thing. So yeah, the scrolling on the screen. Let's actually read this quickly.
I'm glad to hear that the waveform display is now working well for you. Let's move on to the next step. What would you like to work on next? Here are a few possibilities based on our previous discussions. 1. Interactivity. Implementing click detection on the waveforms, where users can click on abnormal segments to generate data. 2. Scoring system. setting up a scoring mechanism where users are rewarded or penalized based on their clicks on normal versus abnormal waveforms. 3. Data storage, saving user interaction data, e.g. clicks, scores, either locally or in a database. 4. UI enhancements, improving the overall user interface, including adding more controls or visual indicators. 5. Mobile optimization, further tweaking the application to enhance usability on mobile devices. 6. Expanding the Flask backend to handle more complex logic or serve additional resources. Let me know which direction you'd like to take, or if you have something else in mind.
That sounds good. So let's just continue step by step. We would like to cover it all. Yeah, interactivity is important. So we would like to implement the click detection, that's for sure. Yeah, the users can click on abnormal segments and not click on normal ones. That would be good for the interactivity. Yes, we definitely want a scoring system. Yeah, I have some point system in mind, but you can suggest your own. That's okay. Storing the interaction data, clicks and scores can be done locally at the moment. That should be fine. So we keep the backend nice and clean. We just keep it as is for now. I don't think we need anything necessarily in the backend at the moment. Mobile optimization, yeah, if we can just do it throughout the development, that would be great. Let's just see it understood and going in the right direction, not hallucinating anything too much.
Let's break this down step by step. We'll start with implementing the click detection on the waveforms, then move on to the scoring system, and finally handle the storage of interaction data locally. Step 1. Implement click detection on waveforms. We'll begin by enabling click detection on the canvas where the waveform is displayed. The idea is to allow users to click on different parts of the waveform, and we'll check whether they clicked on an abnormal or normal segment. Update main.js with click detection. Here's how you can modify main.js to include click detection. JavaScript document.addEventListener, DOM content loaded function.
Okay, next steps. Let's also check it's actually displaying well. Just a few quick things. Can we make the canvas background color different? So if you could generate the style CSS file script, that would be great. Just go step by step. Yeah, we're already calling that the CSS, that's fine. This is what I get. Do you spot any issues? So yeah, the issue with the text, location, and the canvas, and also on the mobile phone, it seems like on a smaller screen, it seems like the waveform still doesn't fit into the canvas, but we have some space below the waveform, so if we can just move all the waveforms down by a fixed amount, that would be great. Let's see if it can sort this for us. It's updating the CSS. Yep, that helped just a bit. And in main.js, it's currently have 73 lines. It's just regenerating the whole thing, or any placeholders? Yeah, there are placeholders in there. Yeah, we have 73 lines. The changing document event listener. Hey, can you regenerate the whole JavaScript main.js script that will run with no errors? It's funny when I talk to the bot for the speech to text work, I actually have to talk more like a robot. So now I'm not sure who's the robot, me or ChatGPT. Okay, main.js. Currently it's 73 lines. I have 76. That sounds promising. Can press it. Shift the waveform down. The vertical shift. Let's make it 30. No. 50. Yeah. No. Uh, 110. Okay, this is better. 110. This value works well for the current waveforms. So that's first that we change manually, but the robot needs to know that we actually changed it. Okay, we don't actually have to margin. Justify content center. We removed this line. Okay, we just made these changes. That's okay. Don't need to change anything, just for your information. And otherwise, with these changes, everything seemed to work pretty well. But we would like to continue developing. Specifically, okay, so currently when we click, there is another message that we need to click OK on. We don't really like it. Yeah, don't do it. We want the application to be self-sustained. We want everything to be within the one page canvas, everything being visible on the screen. We would like the scoring system, the score just to be visible on the screen with a number, and then we'll be adding a rock curve that will keep adjusting live as we play the game. You can just confirm in text, plain text, continuous sentences without any code. Yeah, just confirm. Confirmation and permission. Permission from the robot. Is it okay? Is it okay?
That sounds like a great plan. Moving forward, we'll focus on making the application fully self-contained with everything visible on one screen. Instead of using pop-up alerts, we'll display the score directly on the screen, updating it live as the user interacts with the waveform. We'll also plan to integrate a real-time rock curve that adjusts dynamically as the game progresses. This curve will provide immediate visual feedback on the user's performance, helping them understand their accuracy in identifying abnormal waveforms. With these features, the application will become more interactive and engaging, keeping everything on a single page and providing continuous feedback without any interruptions. We can proceed to implement these elements step by step, starting with displaying and updating the score on the screen.
Okay, it sounds like we on the ball. Can we continue developing? somehow.
Great.
If it understands.
Since we're on track, let's continue by implementing the next steps. We'll start with adding the scoring system that will display the score directly
It's
on the
good that
screen
it's doing
and
it
update
in
it in
text
real time as the
before
user
generating
interacts
code.
with the waveform. Next steps. 1. Add the score display. We'll create a visible element on the screen that will show the current score. 2. Implement the scoring logic. We'll update the score based on user clicks, adding points for correctly identifying abnormal waveforms and subtracting points for clicking on normal ones. 3. Update the UI in real time. The score will update dynamically without needing any pop-ups or page refreshes. 4. Plan for the Rorasi curve. After setting up the scoring, we'll prepare to implement the rock curve, which will dynamically update based on the user's performance. Let me know if you'd like to proceed with the score display and scoring logic, or if there's any other specific feature you want to focus on first.
Okay, so it's actually generated some
Awesome.
code.
Let's get started with adding the score display and implementing the scoring logic.
Yep,
Step
HTML.
1. Add the score display to the HTML. First, we need to create an element in your index.html that will display the score. Here's how you can do it. 1. Update index.html. Add a div element to display the score. Place it above the canvas so that it's clearly visible. HTML body h welcome to cardio. This is where the score will be displayed. Canvas ID equals waveform canvas. Script skills, URL for static file name equal js/waveform.jlgime. This is for static file name as main.jodi. Step 2. Implement the scoring logic in main.js. Next, we'll modify the main.js script to include the scoring logic and update the score in real time. 1. Initialize the score. We'll add a variable to keep track of the score. When the user clicks on the waveform, the score will be updated accordingly. 2. Update the score display. We'll update the inner text of the hashtag score element every time the score changes. Here's what we'll add. Step 3. Integrate scoring in main.js. Now, let's update the main.js file to handle scoring. JavaScript document.eventListener DOM content loaded function. Const canvas equals document.elementById waveform canvas. Const ctx equals canvas.getContext 2D. Let score equals 0. Let current waveform type equals 0. 0 equals normal, 1 equals abnormal. Function to update the score display function update score display. Document.getElementById score. The inner text equals score. Function to resize the canvas based on the window size. Function resize canvas. Canvas.width equals window inner width to 0.9. 90% of the window's width. Canvas height equals window inner.
I don't know why it's reading the text to speech is reading the code. Initialize the score, keep track, clicks. Yeah, we'll update the inner text. Sounds too good to be true. So we'll be making mainly changes to the JavaScript now, hopefully. Will be all the interactions and things. Currently we have 76 lines. Now it's 84, so we know, well, okay. Right, so it's actually working. Yeah, I can click on it. The score goes up. I can click on this one, score goes down. Okay. Yeah, we confirm that the scoring system is working as expected. We can move onto implementing the rock curve that will dynamically adjust as the game progresses. Yeah, so this will be, instead of actually displaying the number of false positive, false negative, true positive, true negative, we'll just add points on a rock curve. Is that correct? Can you just confirm by plain text without any code? Just expand on this bit. Can you make it fun as well? Yeah, give analogies from ECG or EEG data, or potentially even medical imaging, and make it fun in general. I don't know, mention subscribers on YouTube as well, but keep it relevant though. Hopefully it does continue sentences. Doesn't say any. Oh, something about live streaming. Just check briefly that it didn't generate anything too offensive.
Absolutely. The idea here is to create a dynamic Rossi curve that evolves as the player interacts with the game, providing a visual representation of their performance. Instead of showing numbers like false positives, false negatives, true positives, and true negatives directly, we'll plot points on a rock curve that gives immediate visual feedback about how well the player is identifying abnormalities. Imagine you're a biomedical engineer, and instead of just crunching numbers, you're navigating a real-time challenge where every click counts. As you play, you're not just seeing a score number tick up or down. You're actively shaping a rock curve, a powerful tool that's often used in fields like ECG, EEG, and even medical imaging to evaluate the accuracy of diagnostic tools. In this game, your rock curve becomes a living entity on the screen. Every time you correctly identify an abnormal waveform, your curve nudges closer to that coveted top left corner, the sweet spot that indicates high sensitivity and low false positives. Exactly what you want in a diagnostic tool. But beware. Clicking on a normal segment by mistake sends your curve drifting toward the middle, a reminder that even the best engineers have off days. This is where the fun and challenge come in. Just like a YouTuber watching their subscriber count climb with each new video, you'll see your rock curve evolve with every click, reflecting your
It's pretty
growing
good.
skills in real time. And
Damn,
just
this
like with subscribers, one wrong
text is
move could
good.
make you lose some ground, but steady hands and sharp eyes will see you through. So as you play, you'll be developing not just your score, but a visual story of your accuracy. Each
Yeah, we'll
point on the
definitely.
Rocky curve represents a moment of decision, a victory or a setback. Over time, the curve will show whether you're on track to becoming
Okay,
a
well,
top-tier diagnostician or if you need to sharpen your skills further. This makes the game more than just a test of reflexes. It's a true simulation of what it's like to refine a diagnostic tool in the real world. It's about balance, precision, and learning from every click, turning data into insight, just like in the best biomedical engineering practices. When you're ready, we can start building this dynamic rock C-curve into your game, turning your gameplay into a live action evaluation tool that's as fun as it is educational.
yeah, well, sound is a good idea, but there's no sound. What are you talking about? Stop button. No, that's more like future directions. Do we want it now? No, probably not. Okay, so we have. The question is. Yeah, don't like this one because the baseline is not in the same position. No, this is like some overview. What? Yeah, obviously. Yeah, GitHub Copilot doesn't have the GitHub Copilot should be good at turning this into oops, Control I, turn into HTML. Yep. So it's good at doing that, but no, it's really good. Yeah, we're still paying for it, so might as well use it. All those instructions should go at the bottom there. Overview. Okay, can we continue next steps of can we continue with next steps of implementing? So the scoring system is working as expected, but it's not clear, like does it give you a time window to press or not press, like to make a decision? That's what in a previous application we were using a scroll. We were scrolling the waveform over the screen, which essentially will indicate your time to press or not press it. If you have any better suggestions, do let me know. Otherwise, we might use the same thing here. And yes, and we would like to implement the rock curve that will dynamically adjust as the game progresses. Question here, currently there's no essentially time limit for you to press the thing. Let's see what it actually. Let's build. Let's build. Sounds good.
Let's build on what you've described and ensure the game mechanics are clear and engaging while incorporating the dynamic rock curve. Step 1.
Apparently, just discovered I can actually hit the button on my earbuds and it will stop playing. Let's test it.
Clarify the interaction timing mechanism. In your previous application, the waveform scrolled across the screen, which created a natural time window for the player to make a decision to click or not click on a particular segment.
Yeah, this actually works. I can stop it and talk to the robot before it actually continues reading. So this, yeah. So it's the robot is not generating live, it's already generated text. I'm just interacting with the text, commenting on it. So that's pretty good.
This scrolling mechanism works well because it simulates the real-time analysis of an ECG or EEG where signals continuously flow and decisions need to be made quickly and accurately. Options for interaction timing. 1. Scrolling waveform, as before. Mechanics. The waveform scrolls across the screen at a fixed speed, giving the player a limited time to click on potential abnormalities as they appear in the center of the screen. Advantages. This method adds a layer of challenge and urgency, mimicking real-time data analysis. It also provides a consistent experience where the player always knows they have the same amount of time to react.
Well,
Implementation.
it's actually won't be. Actually, in the previous application, it was not the same time to react. Depending on the score, the current score, the speed of the waveform moving across the screen will change. So you can imagine it will go faster if the score is high and will go smaller, shorter. No, will go slower. The waveform will scroll slower if essentially the user is underperforming.
We can implement this by animating the waveform across the canvas. As the waveform scrolls, the player decides whether to click on a segment or let it pass. If they click, it triggers the scoring logic and updates the rock curve. 2. Stationary waveform with timed decision window.
Wait a second. So if the waveform passes on the screen and the user didn't click on it, it should also update the rock curve. We need to make sure it also updates the rock curve.
Mechanics. The waveform remains stationary, but a visual or audio cue, like a flashing segment or a countdown timer, indicates when the player should make a decision. This could involve highlighting specific segments of the waveform for a few seconds. Advantages. This method is slightly more controlled, allowing players to focus on specific segments without the distraction of constant movement. It's easier to implement, but might be less dynamic than the scrolling method. Implementation. This can be done by highlighting parts of the waveform at timed intervals, prompting the player to make a quick decision. The rock curve and score would update based on these interactions. Step 2. Dynamic rock curve implementation. Once the timing mechanism is clear, we can move on to the dynamic rock curve. 1. Rock curve basics. The rock curve will plot the player's performance in terms of true positives, correctly clicking on abnormal segments, versus false positives, incorrectly clicking on normal segments. As the game progresses, each interaction will adjust the curve, giving the player visual feedback on how their decisions are impacting overall accuracy. 2. Live updates. The curve will adjust in real time, with new points being plotted based on each player's decision. If the player correctly identifies an abnormal segment, the curve will move closer to the top left corner, indicating high sensitivity and specificity. Conversely, incorrect decisions will move the curve towards the diagonal, indicating random guessing. 3. Visual representation. The ROC curve will be displayed on the same screen, below or next to the waveform, providing immediate feedback without interrupting gameplay. The curve will help players intuitively understand the impact of their choices, encouraging better performance over time. Step 3. Implementation Plan. 1. Choose interaction timing. Decide whether to continue with the scrolling waveform or implement the stationary waveform with a timed decision window. 2. Set up the scrolling mechanism. If you choose the scrolling waveform, we'll work on animating the waveform across the canvas. 3. Integrate the rock curve.
Okay, so there's a couple of things. Let's go over them one by one. So first of all, yes, we would like the scrolling. It's better than having some sort of counter on the screen. I don't like it. Yeah, I like the interactive aspect and also the fact that we could speed it up and down depending on user performance. So it gives you, the timer goes faster or slower essentially. So we going for the scrolling waveform. We already have something like this implemented, but you could do it yourself from scratch for the current code. I don't know if currently we already have 84 lines of JavaScript code. I don't know if it's an issue or not, perhaps not. So we just keep going, changing this JavaScript code. Now, yeah, so dynamic rock curve implementation sounds good. Live update and visual representation on the same screen sounds good. So ideally both the canvas, the score, and the rock curve will always fit the same screen. They can be vertically arranged on a mobile screen and horizontally arranged on the larger screen. Hopefully you can address this, make it work. Yes, so the implementation plan, yeah, you can choose the interaction timing yourself. Just go, then we might change it later if it's like too slow or too fast. So the waveform will be scrolling right to left across the screen. Hopefully that is straightforward. Ideally, we would have the baseline of the waveform always at the same height on the canvas, if that's possible. Yeah, the rock curve should update real time. Yeah, ensuring that the scrolling speed adjusts dynamically based on the user performance sounds really good. Making it more challenging as they improve and giving them more time to recover if they're struggling or not paying attention or just not skilled enough, so on and so forth. My understanding is that every time a waveform passes, the rock curve will update, add another data point onto it. Hopefully there would be no memory leaks or things like that, so it won't be overwhelming on the web application. It shouldn't be, but just make sure. Yeah, this live incubator, go check it out. It's actually working well at the moment. I just set up like these two incubators, one next to another, and sometimes actually live starts going. Without adding any more water. So we're developing this cardio game. It scrolling ECG waveforms across the screen. You have to label them. We have another version of it where you play against a robot, and we now will be having a third version where it's essentially the basic one, but instead of the performance displayed this way, we'll be displaying a rock curve, a receiver operator curve. Let's read this quickly.
Great. Let's proceed with the implementation plan step by step. Here's how we'll approach it. Step 1. Implement the scrolling waveform. We'll start by animating the waveform to scroll from right to left across the screen. The speed of this scroll will dynamically adjust based on the user's performance. Baseline consistency. We'll ensure that the baseline of the waveform remains at a consistent height on the canvas. Dynamic speed adjustment. As the player's score increases, the waveform will scroll faster. If the score decreases, the scrolling will slow down, giving the player more time to react. Step 2. Integrate the rock curve and score display. We'll integrate the rock curve and score display into the same screen. Real-time rock curve updates. Each time the waveform passes, whether the user clicks or not, we'll add a data point to the rock curve. Vertical and horizontal arrangement. On mobile screens, the elements, canvas, score, and rock curve will be arranged vertically. On larger screens, they'll be arranged horizontally. Step 3. Ensure performance and efficiency. We'll take care to manage resources effectively, ensuring there are no memory leaks and that the application runs smoothly even as the game progresses and the rock curve updates in real time. Implementation steps. 1. Scrolling waveform. Implement a loop that continuously moves the waveform from right to left. Adjust the speed of this loop dynamically based on the current score. 2. Rock curve update. Add a point to the rock curve each time a waveform passes, updating the curve in real time. Ensure that the Rossi curve reflects the player's performance, providing immediate visual feedback. 3. Layout management. Use CSS and JavaScript to ensure that the layout adapts to different screen sizes with vertical and horizontal arrangements as appropriate. Keep the user interface clean, intuitive, and responsive. Next steps. I'll start with the scrolling waveform implementation and integrate it with the existing JavaScript code. Once that's in place, we'll move on to implementing the real-time rock curve updates. This will create a smooth, engaging, and challenging experience that adapts to the player's skill level. I'll handle the memory management aspects to ensure that the game remains performant as it progresses. Let me know if you're ready to proceed, or if there are any additional details you'd like to discuss before we dive into the implementation.
Oh, that sounds really good. Sounds almost too good. So can we start changing the code? Making sure everything works correctly.
Perfect. Let's start by implementing the scrolling waveform feature and then integrate the real-time rock curve updates. We'll update the existing JavaScript code step by step to incorporate these changes. Step 1. Implement scrolling waveform. We'll begin by animating the waveform to scroll from right to left. We'll modify the existing code to include a scrolling mechanism that adjusts its speed based on the user's score. Hack updated main.js with scrolling waveform. Here's the initial implementation. JavaScript document.add event listener DOM content loaded function. Const canvas document get element by ID waveform canvas. Const ctx equals canvas.get context 2D. Let score equals 0. Let current waveform equals. Let current waveform type equals 0. 0 equals normal, 1 equals abnormal. Let scroll position equal to 0. Let scroll speed equals 2. Initial scrolling speed will adjust dynamically. Function to update the score display function update score display. Document get element by ID score. .intertext score score. Function to resize the canvas based on the window size. Function resize canvas. Canvas.width equals window.inner width 0.9. 90% of the window's width.
How to make the scrolling speed faster? I'm increasing the scroll speed number, but it doesn't seem to change anything. Can you explain that bit?
Certainly. The scrolling speed in the current implementation is controlled by two factors. 1. The scroll speed variable. This determines how many positions the waveform shifts per frame. 2. The set interval function. This determines how frequently the waveform is updated, which indirectly affects the perceived speed. How scroll speed works. Scroll speed. This variable defines how many points the waveform should move on each iteration. A higher scroll speed should move the waveform faster across the screen. For example, if scroll speed is set to 2, the waveform will move 2 positions per frame, effectively doubling the speed compared to a scroll speed of 1. Why it might not be changing the speed. If increasing scroll speed isn't noticeably affecting the speed, it could be due to the relationship between the speed of updates, set by set interval, and the scroll speed value. If scroll speed is too low or the updates are too infrequent, the change might not be very noticeable. Adjusting the scrolling speed. To make the scrolling speed more responsive to changes in scroll speed, you can do the following. 1. Increase scroll speed significantly. Ensure that scroll speed has a noticeable impact by using higher values. 2. Adjust the set interval frequency. This controls how often the scrolling function is called. A lower interval means the function runs more frequently, making the waveform appear to move faster. Example adjustments. JavaScript function to scroll the waveform, function scroll waveform. Scroll position equals scroll speed. If scroll position equals current waveform.length, scroll position equals 0, update row, / update the rock curve each time the waveform scrolls completely. Draw waveform. Initialize the game function, initGame. Current waveform type equals generate waveform. Resize canvas, update score display, adjust scroll speed, set interval scroll waveform 25, faster scrolling, more frequent updates. Share explanation, increased scroll speed. If you were using a scroll speed of 2 or 3 and didn't see much difference, try increasing it to 5 or more to see a noticeable effect. Adjusting set interval. By decreasing the interval from 50 milliseconds to 25 milliseconds, the scrolling function is called more frequently, which also makes the scrolling appear faster.
Okay, so we're adjusting the set interval so that the 10 value seem good. What's actually at 10 milliseconds, so that will be that many frames, 100 frames per second speed. So we actually have this in the code now. Now the other question is, we would like them to, the waveforms to actually scroll on the entire screen, coming from the right, going all the way to the left. Currently they just appear and then scroll out. We would like them just to keep scrolling across the screen. Please confirm you understand what I mean. Yes, I understand exactly what you mean. Okay. You want the waveforms to enter the screen from the right side, scroll all the way to the left, and continue scrolling seamlessly without suddenly appearing and disappearing. Yeah, that's exactly right. It's pretty good. It's not pretty good, it's like perfect. Okay. What's that line? There's a weird line. So this is working much better. This, yeah, you did exactly understand what I mean. There's something weird happening. There is this weird line. It's hard to explain. I'll try providing print screens of it. Yeah, if you can look at the images, there's this weird line that is going across the screen. Can we get rid of it? Can you explain where is it potentially coming from? Yeah, those are all abnormal. They're all the same. Uh,
I see what you mean from the screenshots you provided. The issue with the weird line is likely due to how the waveform is being drawn on the canvas as it scrolls across the screen. This can happen if the drawing logic inadvertently connects the last point of one frame to the first point of the next frame, causing an unwanted line to appear. Explanation of the issue. The weird line likely occurs because of how the drawing path is being managed. Specifically, continuity in drawing. If the drawing path isn't correctly managed between frames, the canvas may try to connect the end of one segment to the beginning of the next, causing a stray line to appear. Wrapping around. As the waveform scrolls and wraps around from right to left, if the path isn't reset or properly adjusted, this could create unintended connections between the points. Solution. We can solve this by ensuring that each segment of the waveform is drawn independently without connecting the last point of one frame to the first point of the next. This can be done by resetting the path at the beginning of each draw cycle. Updated code to fix the line issue. JavaScript/function to draw the waveform on the canvas function draw waveform. ctx.clearRect0, canvas.width, canvas.height, ctx.begin path, / start a new path for each draw cycle.
okay, that didn't seem to help. I'll share the current code that I have below. There's also seemed to be an issue, another issue, a major one. So when I hit F5, I get a new random waveform every time. But when they are scrolling, yeah, we need to make absolutely sure that we are not just repeating the same waveform. Can you confirm you understand what I'm talking about?
I understand the two main issues you're facing. One, weird line on the canvas. There's an unwanted line appearing during the scrolling, which wasn't resolved by the previous attempt. Two, repeating waveform issue. Each time the page is refreshed, a new random waveform is generated. But during the scrolling, the waveform might be repeating itself, which you want to avoid. Let's tackle these issues step by step. Issue 1. Weird line on the canvas. If the previous fix didn't resolve the issue, the line might be caused by how the waveform is being wrapped around during scrolling. It's possible that the last point of the waveform is being incorrectly connected to the first point, creating that stray line. To ensure this doesn't happen, we need to be particularly careful with how we manage the drawing logic, especially at the edges of the screen. We might need to look into how the drawing path is being handled and ensure there's no unintended connection between frames. Issue 2. Repeating waveform issue. To avoid repeating the same waveform during scrolling. 1. Continuous waveform generation. We need to generate a longer, continuous waveform that doesn't just loop the same short segment over and over. This can be done by either generating a longer waveform initially or by ensuring that segments of the waveform are concatenated in a way that doesn't produce obvious repetition. 2. Waveform segmentation. Another approach is to dynamically generate new waveform segments as the current one is scrolling off the screen, ensuring a continuous and non-repetitive experience. Steps to address both issues. 1. Update waveform generation logic. We need to ensure that the waveform is long enough to scroll across the entire screen without obvious repetition. If necessary, we can dynamically generate new segments to extend the waveform as it scrolls. 2. Fixing the drawing logic. Revisit the drawing logic to ensure that no unintended lines are drawn as the waveform wraps around the screen. Next steps. If you share the current code you're using, I can help pinpoint where these issues might be coming from and suggest the necessary adjustments to ensure everything works smoothly without the weird lines and with a non-repetitive waveform. Please share the code and we'll go from there.
Giving me two responses. I meant to compare between them. It's funny. It's like it feels like I'm in, the subject in some sort of study where I have to evaluate the performance of the robot or something. Yeah, so which one is better? I don't know. I like the one where it's just an updated code, assuming that works.
Thank you for sharing the code. Let's address both the weird line issue and the waveform repetition issue. Issue 1. Weird line on the canvas. Given the code, the weird line issue might be happening because of how the waveform wraps around when it reaches the end of the screen. When the scroll position resets to 0, the connection between the last point of the previous waveform and the first point of the new one could create an unintended line. To fix this, we'll ensure that the path is reset correctly and that there's no connection between unrelated points when the waveform wraps around. Issue 2, waveform repetition. To prevent the waveform from simply repeating itself as it scrolls, we need to ensure that we're either generating a sufficiently long waveform that doesn't repeat within a single scroll, or dynamically generating new segments as needed. Updated code. Here's how we can adjust the code to address both issues. JavaScript document.add. Thank you for sharing the current code. Based on what you've shared, I can help address both the weird line issue and the waveform repetition issue. Issue 1. Weird line on the canvas. The weird line could be caused by the handling of the drawing path, especially when the waveform scrolls from the end of the canvas back to the beginning. To prevent this, 1. Ensure no connections between segments. We'll need to ensure that each drawing segment starts cleanly without connecting to the previous segment. Let's update the drawing logic to ensure there are no unintended lines. Updated drawing logic to prevent weird line. JavaScript, function to draw the waveform on the canvas, function draw waveform, ctx.clearRect 0, canvas.width, canvas.height, const max value math.max, current waveform, const min value equals math min, current waveform, const.
Okay, that's actually the first thing worked. The line is no longer there, so that's great. Yeah, now with the second problem with extending the waveform to avoid repetition, can we just have it all in the scroll waveform function? I don't think we need two separate functions for this.
Great to hear that the first issue with the line is resolved. Now, let's focus on avoiding waveform repetition by incorporating the logic directly into the scroll waveform function, as you prefer. Consolidated scroll waveform function. We'll modify the scroll waveform function to dynamically extend the waveform within the same function. This will ensure that the waveform does not repeat as it scrolls across the screen. Here's the updated code. JavaScript function scroll waveform. Scroll position equals scroll speed. Check if we need to extend the waveform. If scroll position equals current waveform.length, canvas.width, current waveform.length, const additional waveform equals generate waveform segment. Generate.
While it's reading the code, we have to ask to actually generate the description first and then the code in a separate response. Oh, crap. No. Yeah, that was working, but that's repeating the same waveform over and over. Okay, let's comment that out for a sec. Yeah, it still did do two functions for me. So what's the point? Isn't that the point? That is the point. I'll explain in a sec. Yeah, let's check. No. That's stuffing my stuff up. Wait, go back. Okay, there's a misunderstanding. So currently the line across the canvas is gone, so that's thumbs up. That's really good. Now we want to make sure the same waveform is not repeated again and again. Can we just go over this using plain text? Continuous sentences, full paragraphs, no dot points, no emojis, without any code. We'll generate the code, update the code in the next response. The previous one, stuffing my stuff up. Yeah, so we'll have the life is still going. Yeah, I have these two incubators. Well, I call them incubators, but they're rocks with water, and there is life generated around water, and these two, keep generating life. So yeah, if you play this game, just try generating as much life as possible with using as little water and other resources as possible. So this one seemed to work well, but we'll come back to it in a bit. So we have a couple of versions of this cardio quest or cardio bot, whatever it's called. One simple one that you're supposed to click on the screen on waveforms that do not look right. When you do, you get some points, because we can use humans for training data sets. Well, this data is actually not going anywhere at the moment. It's still in development. And if the ECG waveform looks normal, do not click on it. Then you get points as well by not doing anything. How good is that? Now we have another version of it that does pretty much the same. It has noise options, adding noise option, and but this one will have you competing against the machine. So good luck with that. And now we're doing a third option that will be similar to the first one, but instead of displaying the hits, false alarms, correct rejections, and misses, which are also called true positive, true negative, false positive, false negatives, instead we'll be displaying a rock curve, so a receiver operator curve, and this will be coming shortly. In theory, on long and narrow screens like your phone, they will be coming, it will be underneath the canvas. On wider screens, it will be on the side of the canvas, but we do want to test on smaller screens. And let's see what it says.
I understand that you want to ensure the waveform that scrolls across the screen does not simply repeat itself after completing one cycle. Instead, you want the waveform to continuously evolve, giving the impression of a never-ending dynamic signal rather than a looping pattern. To achieve this, we need to focus on how the waveform is generated and extended. Right now, the waveform likely consists of a fixed set of data points that scroll across the screen. Once all the points have passed, the waveform starts over from the beginning, which creates a repetitive pattern. To avoid this repetition, we can extend the waveform dynamically as it scrolls. Instead of resetting the waveform at the end, we can append new segments to it, effectively making the waveform longer and ensuring that it doesn't simply loop the same sequence over and over. This approach simulates a continuous stream of data, PA, where new information is always coming in, just like in real-world scenarios with ECG or EEG signals. By continuously adding new segments to the waveform as it scrolls, we can create the impression of a constantly evolving signal. This will prevent the player from seeing the same patterns repeat, making the game more engaging and realistic. The challenge will remain fresh as the player encounters new waveform variations throughout the game. Next, I'll provide the code that implements this continuous extension of the waveform, ensuring that it doesn't repeat. This will help keep the gameplay dynamic and challenging, while also avoiding the monotony of a looping signal. It sounds like you're reflecting on a common numerical or logical paradox, where we assign values or meanings to concepts like nothing and something. In many philosophical or mathematical contexts, nothing is often represented by 0 and something by a positive integer like 1. However, when you suggest that nothing could be 1 and something could be 2.1, you're challenging a conventional way of thinking. This idea could be interpreted as a way to redefine our understanding of values or states. In many systems, numbers are used symbolically rather than literally. By assigning nothing the value of 1 and something the value of 2.1, you're creating a system where the baseline or default state is already something, even if it's minimal. In another sense, it might reflect how nothing and something are not absolute states, but rather points.
Okay, and we might not be going deep into philosophy at the moment. The difference between nothing and something. Something is nothing, nothing is something. How about we just stick to the code and actually get it to work? So we get back to the previous prompt. And yes, we would like to implement properly the waveforms, not to repeat one another, but actually alternate. A random fashion is okay. And yes, we can also go into the philosophy of what's really random. Don't ask a mathematician about what's random. We just use, random, like in the simple one. There's always there's always funny business. Let's make sure it's actually understands.
Let's get right back to the code and focus on making sure the waveforms continuously evolve rather than repeating. We'll implement a solution where, as the waveform scrolls across the screen, new segments are dynamically generated and appended to the existing waveform. This will ensure that the waveform doesn't loop back on itself, but instead keeps presenting fresh data. Approach 1. Generate initial waveform. We'll start with a base waveform that will begin scrolling across the screen. 2. Extend the waveform.
Wait a second. So we already have waveforms being generated, so we don't need the generate waveform segment function. We already have it in another JavaScript. I hope you remember. Do you remember? Yeah, we can go into the philosophy of what's remember. Well, obviously the robot has a different understanding of remember. Yes, I remember that you already have waveform generated in our JavaScript. We can utilize the existing logic instead, blah, blah, blah. Instead of creating here, blah, blah, blah. Yeah, we're already doing it. What's the problem? Is scroll waveform. Yeah, we can comment the previous one out. Use that one instead. I don't know why it's not using indentation properly. Again, don't ask a Python program about indentation. They will go on and on about that as well. Let's read that quickly before I'm losing my voice.
Yes, I remember that you already have waveform generation code in another JavaScript file. We can utilize that existing logic instead of creating a new generate waveform segment function. Here's how we can adapt the scroll waveform function to dynamically extend the waveform using your existing generation logic. We'll incorporate your existing waveform generation function directly into the scrolling logic. When the waveform is about to repeat, we'll call your existing function to generate a new segment and append it to the current waveform. Updated code implementation. Here's how you can modify the scroll waveform function. JavaScript/function to scroll the waveform. Function scroll waveform, scroll position plus scroll speed. Check if the waveform is close to repeating and extend it using your existing generation function. If scroll position equals current waveform.
Okay, we stuffed something up really badly. So it was working okay before, the scrolling was fine, but it was scrolling the same waveform over and over again, pretty sure. But now, yeah, we're exceeding the maximum call stack size. So this page is currently loading 132 megabytes. That's not ideal, is it? Can you fix the code? We just want to select a random waveform from our waveform JavaScript code and scroll it on the screen one at a time. Is it too hard? I don't know. They're all the same, aren't they? Yeah, pretty sure. So that's not fun.
It seems like there was an issue with the way the waveform was being extended, leading to the excessive memory usage and the maximum call stack size exceeded error. This is likely due to the waveform continually growing without proper management, resulting in the browser running out of memory. Let's simplify the approach. Objective. We'll select a random waveform from your existing waveforms.js code and scroll it across the screen one at a time without causing it to repeat unnecessarily or exceed memory limits. Plan 1. Randomly select a waveform. At the start of the game, select a random waveform from the available waveforms in your waveforms.js file. 2. Scroll the selected waveform. Scroll this selected waveform across the screen. Once it has fully scrolled across, select a new waveform. 3. Prevent repetition. Ensure that each waveform scrolls fully before selecting a new one. Simplified implementation. Here's how we can achieve that. JavaScript document.addEventListener DOM content loaded function. Const canvas equals document get element by ID waveform canvas. Const ctx canvas get context 2D. Let score equals 0. Let current waveform equals v. Let current waveform type equals 0. So 0 equals normal, 1 equals abnormal. Let scroll position equals 0. Let scroll speed equals 2. Initial scrolling speed will adjust.
Okay, currently there seems to be a problem with the new code that the waveform is just changing midway, essentially halfway through scrolling past the canvas. it's just all of a sudden selecting a different one. Can we address that? Also, one of them is weirdly inverted or something. Yeah, I don't know what's up with that one.
The issue you're describing happens because the new waveform is being selected as soon as the scroll position reaches the end of the current waveform. If If this happens while the waveform is still visible on the canvas, it might result in the waveform abruptly changing before it has fully scrolled out of view. We need to ensure that the current waveform scrolls completely off the canvas before selecting a new one. To do this, we should delay selecting a new waveform until the entire waveform has exited the visible area of the canvas. Adjusted approach. Instead of selecting a new waveform as soon as scroll position reaches the end of the current waveform, we'll wait until the entire waveform has scrolled out of view. This means we'll only select a new waveform once the last point of the current waveform has moved completely off the left side of the canvas. Updated code implementation. Here's how you can modify the scroll waveform function to address this. JavaScript / function to scroll the waveform function scroll waveform, scroll position = scroll speed. Check if the waveform has fully scrolled out of view before selecting a new one. If scroll position current waveform.length canvas.width canvas.width current waveform.length, scroll position = 0, select random waveform. Select a new random waveform update rock. Update the rock curve each time the waveform scrolls completely. Draw waveform. Explanation. Delay new selection. The key change is in the condition that checks whether to select a new waveform. We now wait.
Okay, so currently there are multiple similar waveforms are being scrolled before another one is selected. Hey, can we change the approach entirely and try something else? Hey, can you describe the changes first in plain text, full sentences, and then we will generate the code in the next prompt? And while it's generating, go check out bionichaos.com, 1C. Can never get the name right, the speech to text. Should have. Also have a bunch of other domains that probably also would not be able to get the name correctly. Yeah, we also have Bionic Cloud, which we haven't touched in a while. The idea for it potentially was to have this application, but yes, require login, which I really don't want to do, but maybe we'll have to at some stage, and essentially have access to the tools without advertisement. But we see how we go.
Certainly. Here's the new approach in detail. Overview of the new approach. 1. Preloading and shuffling waveforms. Before starting the scrolling, we'll load all the available waveforms into an array. This array will represent a queue of waveforms that will be scrolled across the screen one by one. To ensure variety, we'll shuffle this array at the start. Shuffling ensures that the waveforms are presented in a random order, but each waveform is fully scrolled across the screen before the next one begins. 2. Sequential scrolling. Instead of dynamically selecting a new waveform during the scrolling process, we'll use the preloaded queue of waveforms. Each waveform will be scrolled fully across the screen. Once it has completely exited the screen, the next waveform in the queue will start scrolling. This method ensures that no waveform is interrupted or changed midway, and each waveform gets a complete pass across the screen. 3. Looping through the waveforms. After all waveforms in the queue have been scrolled, we'll reshuffle them and start the process again. This looping mechanism ensures that the game can continue indefinitely, with the waveforms being presented in a random, non-repetitive order. Summary. This approach solves the issue of waveforms changing midway by using a preloaded and shuffled queue of waveforms. Each waveform is scrolled completely across the screen before a new one is selected, ensuring a smooth and varied presentation. After all waveforms have been displayed, the process repeats, maintaining variety throughout the game. In the next step, we will implement this approach in code. Let me know if you're ready to proceed. Certainly. Let's take a step-by-step approach to regenerate the code from scratch to ensure it's working as expected. We'll focus on scrolling one waveform at a time across the screen, selecting a new waveform only after the current one has fully scrolled off the screen. Step-by-step plan. 1. Initialize the game. Set up the canvas and context. Initialize the score and scrolling parameters. 2. Load and shuffle waveforms. Load all available waveforms into an array. Shuffle the array to ensure that the waveforms are displayed in a random order. 3. Scroll waveforms. Scroll each waveform fully across the screen before selecting the next one. Ensure that the waveform scrolls smoothly from right to left. 4. Select next waveform. Once the current waveform has fully scrolled out of view, select the next one from the shuffled array. 5. Handle clicks and adjust speed. Handle user interactions and adjust the scrolling speed based on the current score. Code implementation. Here's the code based on the plan above. JavaScript document.addEventListener, DOM content loaded function. Const canvas equals document.getElement. Let's revisit the implementation from scratch to address the issues you're experiencing with waveform scrolling. We'll focus on ensuring that each waveform is scrolled completely across the screen before the next waveform begins, and that the transition between waveforms is smooth. Revised Plan 1. Waveform queue. We'll maintain a queue of waveforms to be displayed. Each waveform will be completely scrolled before the next one starts. 2. Waveform generation. At the start, a set number of waveforms will be generated and stored in the queue. This ensures a smooth transition between waveforms without repeated generation during the scroll. 3. Scroll completion. We'll make sure to only load the next waveform when the current one has completely exited the screen. 4. Memory management. To avoid memory issues, we'll ensure that waveforms are not extending in size during scrolling, preventing potential memory overflow. Implementation steps. 1. Setup and initialization. Initialize variables for the canvas, context, and waveform data. Set up the canvas dimensions and event listeners. 2. Waveform queue management. Preload a few waveforms into a queue. Implement logic to fetch the next waveform when the current one has finished scrolling. 3. Drawing and scrolling. Draw the waveform starting from the right side of the canvas and scroll to the left. Ensure that when the end of a waveform is reached, the next waveform starts after the current one has completely disappeared from view. Proposed code. Here is a simple version of the revised code. JavaScript document.addEventListener DOM content loaded function. Const canvas equals document get element by ID waveform canvas. Certainly. We can use the scrolling logic and the option to add noise from the provided gamelogic.js code as a foundation. Here's how we can approach this. Key elements to integrate. 1. Scrolling logic. The logic in the game loop function effectively handles the scrolling of the waveform across the screen. We will retain this functionality, making sure the waveform scrolls smoothly from right to left. 2. Noise addition. The code already includes a noise level variable, which allows you to add noise to the waveform dynamically via a slider, noise slider. We will retain and integrate this feature to ensure that noise can be added or adjusted during gameplay. What we'll do. 1. Retain the working scrolling logic. We'll keep the existing logic for scrolling the waveform, ensuring that the waveform moves smoothly across the canvas. 2. Integrate noise addition. We'll make sure that the noise level can be adjusted using the slider and that the waveform can be rendered with the added noise as it scrolls. Steps 1. Extract and modify scrolling logic. We'll take the scrolling logic from your game loop function and ensure it integrates seamlessly into your game. 2. Implement noise integration. We'll ensure that the noise slider works correctly, dynamically adjusting the waveform as it scrolls. Next step, we'll modify the code to ensure that these features are implemented correctly, and I will provide the integrated code for you to use. Would you like to proceed with generating the full integrated code, or do you have any specific adjustments or requirements before we proceed?
The score is just a score. And so we have one score. The waveform canvas is just a general size. The size is not specified in the HTML. The size should be controlled by the JavaScript. And yes, in controls we have a noise slider. That's fine. And we have the rock curve canvas. And again, the size of it, the dimensions of that canvas could be controlled by the JavaScript. Now we also don't need the waveform analysis bit. So we're not doing that. So we just want the simple game. The scrolling should work, and we have a rock curve and the score, so 3 elements only. Sorry, and the noise as well, the noise controller. Also, we want the CSS to be in a separate file. Let's update HTML first. Can we update the JavaScript as well? Can we do the next step of updating and regenerating the JavaScript code? There's currently a problem. So generally it seems to work okay. There are no errors. The scrolling is working well, and the score seemed to show correctly, except that I cannot tell because the waveform is essentially outside the canvas area. It's way above. It's way too high. So I can only see the bottom tip of the waveform. Waveform. Waveform.
The issue you're describing is likely due to the vertical positioning of the waveform on the canvas. If the waveform is starting too high on the canvas, only the bottom part of it will be visible. To fix this, we need to adjust the waveform Y value in the draw waveform function to ensure the waveform is centered vertically or positioned within the visible area of the canvas. Adjusting the vertical position. The simplest approach is to ensure that the waveform Y value places the waveform correctly within the canvas height, accounting for the waveform's amplitude so it fits within the visible area. Updated code with vertical adjustment. JavaScript document.addEventListener DOM content loaded. Const canvas document get element by ID game canvas. Const rock canvas document get element by ID rock curve canvas. Const ctx equals canvas.get context 2D. Const raw ctx equals rock canvas.get context 2D.
Okay, this is a bit better. We would like to. I can see some of the waveform, but we need it to be adjusted even lower, probably by the same amount as before. Also, the noise level, it should not be random while the waveform is displaying. It should be set the noise should be just added to the waveform, and it should be the same as it's scrolling through the screen. Can you make sure? Can you confirm you understand what I mean? How does asking the question of if you understand the requirements even, what does it even mean? Like, would it ever say, no, I don't understand the requirements? Let's actually check if it's any in. Adjust the position. So if I go 0.5, adjust it even further. No. One just works. Are those different waveforms? This was the same. This is different. It's still abnormal. This should go 50. Yep, looks pretty good. No, that's actually pretty good. I did change, however, the following line to be just multiplied by 1. I don't know why it had 0.75 or 0.5 before. Don't matter. Doesn't matter. It actually works. This is the new line just for your reference. We don't see the rock curve at the moment, as you're probably aware. Can you explain in text the next steps before generating the code?
Great to hear that the waveform positioning is working well with your adjustment. Now, let's focus on getting the rock curve to display correctly. Next steps for displaying the rock curve. 1. Setting up a rock curve data. The Roxy curve is typically plotted using data points that represent the true positive rate, sensitivity, against the false positive rate, 1 specificity. We need to accumulate data on hits, true positives, misses, false negatives, false alarms, false positives, and correct rejections, true negatives, as the game progresses. 2. Calculating raw C points. For each completed waveform interaction, after each waveform has fully scrolled off the screen, calculate the sensitivity and specificity. Convert these into a point on the ROS curve, x equals false positive rate, y equals true positive rate. 3. Plotting the ROS curve. Use the ROS curve canvas to plot these points as the game progresses. We'll start with an empty canvas and plot points dynamically as the player interacts with more waveforms. 4. Ensuring visibility. Make sure the Roxy curve canvas is being cleared and redrawn each time a new point is added to the curve. We'll need to properly scale the rock curve to fit within the canvas dimensions. Approach 1. Accumulate data. Track the number of hits, misses, false alarms, and correct rejections. 2. Calculate points. Convert these into rock curve points after each waveform interaction. 3. Draw a rock curve. Plot the points on the Rossi canvas, connecting them with lines for a continuous curve. Next step. Would you like to proceed with implementing the rock curve plotting code now? Or do you have any specific preferences or additional details you'd like to consider before generating the code?
If you made the one mistake, it's a bit suspicious, because there could be other ones as well. Other ones as well. Other. It's really pissing me off. Hey, can you explain in text only, without any new code? Why do I get an error? And are there any other issues with this code?
The error you're encountering, uncaught reference error, waveform counted is not defined, occurs because the variable waveform counted was used in the code, but it wasn't declared anywhere. This would cause the JavaScript engine to throw an error since it tries to reference a variable that doesn't exist. Explanation of the error. 1. Missing declaration. The waveform counted variable is used to track whether a waveform has been counted for scoring purposes. However, in the provided code, it was never declared using let, const, or var. Without this declaration, the variable doesn't exist in the scope, leading to the reference error. Hash potential issues. Given that this variable was missed, there could be other similar issues in the code. Here are a few things to watch for. 1. Variable declarations. Ensure all variables are properly declared. Anytime a variable is used, it must first be declared within the correct scope. 2. Scope. Let's go through the code step by step to identify potential issues.
Yeah, let's do that. Let's go through the code.
Starting with the error you've encountered and then examining other parts of the code. 1. Waveform counted declaration. Issue. The variable waveform counted is used but not declared. This leads to a reference error. Solution. Ensure that waveform counted is properly declared at the beginning of the script or within the appropriate scope. It should be declared along with other game state variables like hits, misses, etc. 2. Variable declarations. Review. All variables should be declared with let, const, or var before they are used. This includes waveform counted, current waveform clicked, and any other variables that might be referenced across functions. Potential issue. Other variables such as current waveform clicked and noisy waveform should also be reviewed to ensure they are declared correctly in the appropriate scope. 3. Scope of variables. Scope check. Variables that are used across multiple functions, like waveform.
Okay, can you check the code and regenerate one that works with no errors? That would be nice. He's swearing. This one will not return any errors. We had just before we had like 150 lines. Now we have 172. This one 175. Okay, so it just declared the variables we haven't declared before. Is that it? Okay, it's actually working. Can scroll is a bit funny. The scroller. Okay, now the speed is 0, so it's essentially the same thing as what we had before. This should give us 20. Yep, give us 30. That's fine. If we don't click on this, it should reduce down to 20. That's correct. That's 30. That's fine. The normal one should give us 40. If another normal one should give us 30 if we actually click on that. So that's all good. Where is okay, everything seemed to work correctly. But I don't see the rock curve. Can we do something about this? We do have the rock curve canvas, and that's what it's called. Yeah, proceed with these steps and debug. There are no errors whatsoever, so that's a good sign. Something isn't working because the rock curve is not there. Can you explain in plain text continuous sentences, full paragraphs without any code? What changes were made and what was wrong before that the rock curve did not appear? Well, happy to try. There's only one way to know if it's working or not. We have 175 lines of code and now 183. Getting longer and longer. It doesn't necessarily means it's better and better. Okay, we should have something there. Um, yeah, it's running. We have values, but no values appear on the curve. Is there something wrong with styling or something? The values seem to be there, but I don't see anything appearing on the rock curve. Also, one possible issue is that currently we have nothing in style CSS file. So can we regenerate the CSS script? Maybe that will help. I don't see any errors at the moment.
It looks like the rock points are being calculated and logged correctly, but they aren't appearing on the canvas. This could indeed be related to the lack of styling for the canvas elements. Let's regenerate the style.css file to ensure that everything is properly styled, which might resolve the visibility issue. Regenerated style.css. Here's a basic style.css that provides the necessary styling for your canvas elements and overall layout. CSS body, font family, Arial, sans serif, margin 0, padding, display flex, flex direction column, align items center, background color F4, 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 color 333. H1, font size 24px, margin 20px 0, text align center. Game canvas.
There's still nothing on the rock curve canvas. We added the style CSS script. And this is also what we have for HTML and Python. I wonder if it needs any adjustments.
Thank you for sharing the HTML and Python code. It seems like everything is correctly set up on that front, and the rock C points are indeed being generated. Given that the points are being logged correctly in the console but still not appearing on the rock curve canvas, the issue likely lies in the way the points are being plotted or in how the Rossi canvas is handled. Possible issues. 1. Canvas overlap or sizing. The rock curve canvas might be overlapping with other elements or not correctly sized, causing the drawn points to not be visible. 2. Scaling of rock points. The points might be plotted outside the visible area due to incorrect scaling or offsets. Steps to diagnose and fix. 1. Inspect the rock canvas. Ensure that the ROC canvas is correctly sized and not being covered by other elements. You can try giving the canvas a background color temporarily to see if it's correctly displayed on the page. 2. Adjust the ROC point scaling. Review the scaling logic to ensure that the points are within the visible area. You might need to adjust the scaling factors or add margins to ensure the points fall within the canvas. 3. Temporary debugging enhancements. Set a background color for the rock canvas in the CSS to ensure it's visible. Temporarily plot fixed points on the rock canvas to verify that it can display points correctly. Updated approach. Let's start by confirming the rock canvas is visible and correctly sized by setting a background color and then checking the rock point scaling. 1. CSS update. Add the following to your style.css to give the rock canvas a visible background and border. CSS hash rock curve canvas. Background color E00. Light gray background to see the canvas. Border 2px solid 000. Black border to distinguish the canvas. 2. Temporary rock points for testing. You can temporarily modify the draw rock function to plot a few fixed points on the canvas. This will help ensure that the canvas is correctly drawing points. Once you do these steps, check again if the rock curve is visible. If it's still not displaying correctly, we'll dive deeper into the point scaling and drawing logic.
Seems like we're not getting much further. And no, there's no points. No, I added the modified draw rock function, but there's no points appearing on the canvas. Wait a sec, let's do it with the CSS adjustment as well. There's something appearing and disappearing. Must be clearing it or something. Well, they don't appear properly, but there's something flashing on the rock curve canvas, but then it's disappearing quickly, so I can't really see what it is. Should be an easy fix. Well, that's everything else, isn't it? Nothing is ever easy fix.
What you are observing on the rock curve canvas is likely a result of how the ROS points are being calculated and plotted. The line seems to be moving in a way that doesn't create a coherent rock curve, which suggests that the points being plotted may not be accurately representing the intended rock characteristics. What is happening? 1. Plotting points at same locations. The points being plotted on the Rossi curve canvas are very close together, or possibly even at the same location, which could explain why you're seeing a line moving or fluctuating rather than a clear curve. This could be due to the way the true positive rate, TPR, and false positive rate, FPR, are being calculated. Number 2. Points fluctuating. The fluctuation you're seeing could be due to small changes in the calculated values of TPR and FPR, which are causing the line to move slightly each time a new point is plotted. 3. Limited movement. If the TPR and FPR values are staying within a very narrow range, it would cause the line to stay close to the center or one side of the canvas, which doesn't represent the full potential of the ROC curve. Why the line moves like that? ROC point calculation. The ROC curve is based on the relationship between the true positive rate, TPR, and the false positive rate, FPR. If the calculations for these metrics are not showing significant variance, the points will cluster tightly together on the canvas, resulting in the small fluctuations you see rather than a more distinct curve. Canvas scaling. The scaling of these values to fit the canvas might also be contributing to the odd behavior. If the FPR and TPR are very small or large, the plotted points might not spread out enough across the canvas, making the line look less like a curve and more like a jittery line. Next steps. 1. Check ROC calculation. We should review how the TPR and FPR are being calculated and whether they are correctly reflecting the player's performance. 2. Adjust rock scaling. Adjust the scaling to ensure that even small changes in TPR and FPR result in more noticeable movement on the canvas. 3. Ensure diverse rock points. We may need to ensure that the game logic produces a variety of TPR and FPR values to create a more informative and spread out rock curve. Plan. 1. Review and adjust the rock calculation logic. 2. Test with different scaling factors. 3. Add debugging to verify diverse points are being generated. Would you like to proceed with these steps to refine the rock curve plotting? Let's proceed with refining the rock curve plotting by addressing the issues with rock point calculation, scaling, and ensuring diversity in the points plotted. Steps to refine the rock curve plotting. 1. Review and adjust the rock calculation logic. We will first ensure that the true positive rate, TPR, and false positive rate, FPR, are calculated correctly and represent diverse values. This is crucial for plotting a meaningful rock curve. TPR, true positive rate, represents the ratio of correctly identified abnormal waveforms, hits to the total number of actual abnormal waveforms, hits plus misses. FPR, false positive rate, represents the ratio of incorrectly identified normal waveforms, false alarms, to the total number of actual normal waveforms, false alarms plus correct rejections. If the game logic does not allow for enough variability in these metrics, the ROC points will cluster together, resulting in the line you see. 2. Adjust ROC scaling. Next, we'll refine the scaling of TPR and FPR to the canvas dimensions. This involves ensuring that small changes in TPR and FPR lead to more noticeable movements on the canvas, creating a more dynamic and spread out curve. We will adjust the multiplication factors when scaling the TPR and FPR to the canvas width and height, ensuring that even small differences result in visible changes on the canvas. Add debugging to verify diverse points. We'll continue to log the TPR and FPR values to the console and visually check if they are diverse enough. If the values are too similar, we may need to adjust the game logic to ensure more variety. Updated code. Below is an updated version of the relevant part of the code with adjustments for more noticeable rock plotting. JavaScript Explanation of the new code. The recent code update focused on improving how the ROC, receiver operating characteristic curve, is drawn on the canvas, ensuring that the true positive rate, TPR, and false positive rate, FPR, are calculated correctly and that their values are scaled appropriately to fit the canvas. Key elements of the code, TPR and FPR calculation. True positive rate, TPR. This is the ratio of correctly identified abnormal waveforms, hits, to the total number of actual abnormal waveforms, hits plus misses. False positive rate, FPR. This is the ratio of incorrectly identified normal waveforms, false alarms, to the total number of actual normal waveforms, false alarms plus correct rejections. 2. Drawing the ROC curve. The code calculates ROC points based on the TPR and FPR and then plots them on the canvas. The points are scaled to fit the canvas dimensions, with the FPR mapped to the x-axis and the inverted TPR, 1 minus TPR, mapped to the y-axis. This inversion ensures that a perfect classifier would produce a point in the top left corner of the canvas. 3. Debugging output. To assist in troubleshooting, the code logs each rock point's coordinates to the console as it is drawn, allowing you to verify that the points are being calculated and plotted correctly. Explanation of the image. The image you provided shows a sequence of rock points plotted on the canvas. The points form a stair-step pattern, which reflects how the rock curve is built up incrementally as new points are plotted. What the stair-step pattern indicates. The stair-step pattern typically occurs when the ROC points are closely spaced, with small changes in TPR and FPR from one point to the next. This could mean that the player's performance is gradually improving or deteriorating, causing incremental changes in the TPR and FPR values. The curve is not smooth because we are currently plotting the points and connecting them with straight lines as they are generated. Should we fit a curve to the data points? Yes, fitting a smoother curve to the data points can make the Rossi curve more visually representative of the underlying trends in the data. A smooth curve can better convey the overall performance of the classifier, or in this case, the player, by minimizing the visual noise from small incremental changes in the TPR and FPR values. Next steps. 1. Plot points first. Continue plotting the Rossi points as they are generated, just as we have been doing. This allows us to visualize the raw data and ensure that the points are being calculated correctly. 2. Fit a curve to the points. After plotting the points, we can implement a curve-fitting algorithm, such as a spline interpolation or a Bezier curve, to draw a smoother rock curve. This will make the curve easier to interpret and more visually appealing. 3. Test the curve fitting. We can test the curve fitting on the current set of points and observe how it affects the appearance of the Rossi curve. If the fitted curve better represents the player's performance, we can keep it. Otherwise, we can revert to the stepwise approach. Would you like to proceed with fitting a curve to the ROC points? If so, I can guide you through implementing a simple curve fitting algorithm. Certainly. Let's describe how we'll modify the code to achieve the desired behavior for the Rossi curve. Desired behavior. 1. Initial state. The ROC curve should start as a flat line where x equals y. This means that if there are no data points, the Rossi curve will appear as a diagonal line from the bottom left corner, 0, 0, the top right corner, 1, 1 of the canvas. This line represents a random guess classifier, where the true positive rate, TPR, is equal to the false positive rate, FPR. 2. Scatter plot of points. As the game progresses and Rossi points, representing different TPR and FPR values, are generated, these points should be plotted as individual data points on the canvas, like a scatter plot. These points should not be connected by lines. 3. Dynamic adjustment of the Rossi curve. As more data points are added, the flat line will remain as a reference, or potentially be removed if you decide it's unnecessary. But the scatter plot of ROC points will start showing how well the player is performing. Over time, these points should ideally move closer to the top left corner if the player is performing well, indicating a high TPR and low FPR. Implementation plan. 1. Flat line, x equals y. We will first draw a flat line from the bottom left to the top right of the ROC canvas to represent the x equals y reference line. This line will stay on the canvas and serve as a baseline to compare against the player's performance. 2. Plotting rock points as a scatter plot. We will modify the existing drawRock function to plot each rock point as a dot on the canvas rather than connecting the points with lines. Each point will represent the TPR and FPR at a given moment. 3. Avoiding line connections. We will remove the logic that connects rock points with lines. Instead, the drawRock function will only plot individual points, allowing you to see the distribution of rock points over time. 4. Updating the canvas. Each time a new point is generated, the rock canvas will be updated to include the new point, but without clearing or redrawing the previous points, other than the initial flat line. This will allow the scatter plot to accumulate on the canvas. 5. Potential enhancements. We could add a color gradient to the points based on how recent they are, or a tooltip to display specific TPR, FPR values when hovering over a point, though these enhancements would come after the basic scatterplot functionality is working. Summary of changes. Draw a static line x equals y pi how on the Rossi canvas to represent a random guess classifier. Plot rock points as individual dots on the canvas without connecting them with lines. Ensure the Rossi canvas is not cleared after each update, allowing the scatter plot to build up over time. Would you like to proceed with implementing these changes in the next prompt?
Yeah, so it's actually working pretty well. Well, when I say well. Yeah, we can explain it and everything, but it's moving around. It actually makes sense. So we might just add the y and x labels for the rock curve. We'll add more description, and we will let you, we'll publish it so you can play with it as well.
The rock points are now appearing on the canvas as individual dots, and the scatter plot is beginning to take shape. However, it looks like the points are clustering in the lower left corner of the rock curve, which might indicate an issue with how the TPR and FPR values are being calculated or scaled. What's happening? Point clustering. The clustering of points in the lower left could suggest that most of the rock points have a low TPR and FPR, indicating that the player's decisions are not leading to high sensitivity or specificity. Reference line visibility. The reference line x equals y is visible, but the Rossi points are currently concentrated in a small area, not taking full advantage of the canvas space. Next steps. 1. Review TPR and FPR calculation. Ensure that the calculation of TPR, true positive rate, and FPR, false positive rate, is accurate and reflective of the player's performance. If the points are clustering in the lower left, it suggests that both rates are low, meaning the player might be missing abnormal signals and not identifying normal ones correctly. 2. Adjust scaling. We may need to adjust the scaling to spread out the points more across the canvas. This could involve tweaking how the TPR and FPR values are mapped to the canvas coordinates. 3. Consider adding more visual feedback. If the points continue to cluster, we could add additional visual feedback, such as highlighting specific points when the player makes a mistake or performs well. 4. Debug and refine. It might be helpful to add more debugging information to verify that the rock points are being calculated correctly and see if there is any pattern in when the points cluster. Would you like to proceed with reviewing and potentially adjusting the TPR and FPR? Looking at the latest image, it seems like the rock points are still clustering in the lower left area, which indicates that both the TPR, true positive rate, and FPR, false positive rate, values are relatively low for most of the plotted points. Potential reasons for clustering. 1. Player performance. If the player is consistently making decisions that result in both low TPR and FPR, the Rossi points will naturally cluster in the lower left of the rock space. This could be indicative of a cautious approach where the player is not frequently identifying waveforms as abnormal, leading to low sensitivity, TPR, and low specificity, FPR. 2. Calculation or scaling issues. There might be a subtle issue in how the TPR and FPR values are being calculated or scaled. If the scaling factors are too small, even slight variations in TPR and FPR might not spread out the points enough on the canvas. Suggested steps. 1. Review TPR and FPR calculation. Double-check that the calculations for TPR and FPR are accurate and that they reflect the true performance of the player. The formulae being used are correct, but we need to ensure that the game logic supports a wide range of TPR and FPR values. 2. Adjust scaling factors. We might want to experiment with different scaling factors to see if it helps spread the points out more across the rock space. This can be done by adjusting how we map the TPR and FPR values to the canvas coordinates. 3. Monitor and log values. Continue to log TPR and FPR values to the console to ensure that a variety of values are being generated. If most values are very low, this might explain the clustering. Plan. Increase scaling sensitivity. We can adjust the scaling to make even small changes in TPR and FPR more visible on the canvas. Re-examine player feedback. We might need to ensure the player has enough incentive to explore a wider range of actions, leading to a broader spread of Rossi points. Would you like to proceed with adjusting the scaling factors and further debugging the rock curve behavior? If you're seeing consistent clustering despite making a variety of decisions, then focusing on scaling might be the right next step. The provided code is structured to handle the core functionalities of your ECG game, including the rock C-curve plotting, waveform drawing, and score updates. Below is an explanation of each key section and how the code operates. Key functionalities: canvas setup and resizing. The game and rock canvases are initialized and resized based on the window's size. This ensures that the game scales appropriately across different screen sizes. 2. Waveform handling. Apply noise to waveform. This function adds noise to the waveform, making the game more challenging. Draw waveform. This function draws the noisy waveform on the canvas. Clear game canvas. Clears the canvas for the next frame of the game loop. Handle click. Detects when the user clicks on the waveform and updates the score accordingly. 3. Score and game logic. Update score. Updates the score based on hits, misses, false alarms, and correct rejections. Update correct rejections and misses. Handles the logic for counting correct rejections and misses. Calculate ROC points. Calculates the true positive rate, TPR, and false positive rate, FPR, for plotting the rock curve. 4. Rock curve plotting. Draw a rock reference line. Draws a baseline rock curve, a straight line from 0, 1 to 1, 0 as a reference. The provided code manages the various aspects of your ECG game, including waveform generation, scoring, and plotting the rock C-curve. Each part of the code plays a crucial role in making the game interactive and visually informative. The main functions are designed to handle specific tasks, such as drawing waveforms, updating scores, and plotting the Rossi curve based on the player's performance. Canvas setup and resizing. The game uses two canvases, one for displaying the ECG waveform and another for plotting the rock curve. The canvases are dynamically resized to fit the screen, ensuring that the game is responsive and adapts to different screen sizes. This resizing happens automatically whenever the window size changes, making the game accessible on various devices. Waveform handling. The waveform handling section includes functions for generating and displaying the ECG waveforms. The apply noise to waveform function introduces variability by adding noise to the waveform, which increases the game's difficulty. The waveform is then drawn on the canvas using the draw waveform function. The game clears the canvas before each new frame, ensuring that the waveform scrolls smoothly across the screen. When the player clicks on the waveform, the handle click function determines whether the click was on an abnormal or normal segment, updating the score accordingly. Scoring and game logic. Scoring is a key component of the game, and the code carefully tracks the player's performance. The update score function calculates the score based on the number of hits, misses, false alarms, and correct rejections. The game also includes logic for tracking correct rejections and misses, which ensures that the player's decisions are accurately reflected in the score. This logic is crucial for maintaining a challenging and engaging gameplay experience. Tashad rock curve plotting. The rock curve provides a visual representation of the player's ability to distinguish between normal and abnormal waveforms. The code first draws a reference line on the Rossi canvas, representing a random classifier where the true positive rate, TPR, equals the false positive rate, FPR. As the game progresses, the update rock function adds new points to the rock curve based on the player's performance. Each point is plotted as a small dot on the canvas, with the TPR and FPR determining its position. This scatter plot grows over time, giving the player immediate feedback on how well they are performing. Game loop. The game loop is the engine that keeps the game running. It continuously updates the game's state, moves the waveform across the screen, and checks for player interactions. This loop ensures that the game is responsive and that the waveform scrolls smoothly from right to left. The loop also handles the timing of updates, making sure that the game runs at a consistent speed. Current behavior and next steps. Currently, the Rossi curve points are clustering in a specific area, which suggests that the TPR and FPR values are not varying enough. This could be due to the player's performance or the way these values are calculated and scaled. To address this, it would be beneficial to review how TPR and FPR are calculated to ensure they accurately reflect the player's actions. Adjusting the scaling of these values might also help spread the points more evenly across the Rossi canvas. Additionally, providing more immediate visual feedback to the player could enhance the gameplay experience. This feedback would help players understand how their actions influence the rock curve, making the game more engaging and educational. Moving forward, focusing on these areas will help refine the game and improve the accuracy and visual appeal of the rock curve.
Yeah, so it's working okay at the moment. So there's a couple of things. Can we also talk about fitting an actual line to the data points? We potentially want to put them in different colors. So correct responses in green and incorrect responses in red on the canvas. So hopefully that should be an easy fix. What else can we do? And we want labels to the X and Y axis to actually be shown on the screen.
The current code effectively handles the core functions needed for your ECG game, such as waveform generation, noise application, score updates, and a rock curve plotting. However, there are several areas where it could be optimized or enhanced to improve performance, user experience, and maintainability. Optimizing the waveform handling. The current approach for generating and applying noise to the waveform is straightforward, but it could benefit from some improvements. One suggestion would be to pre-calculate the noisy waveform rather than recalculating in it during each frame of the game loop. This would reduce the computational load during the game loop, making the scrolling smoother, especially when the game speed increases. Additionally, consider adding more control over the noise application by allowing different types of noise to be applied: Gaussian noise, uniform noise. To introduce variability and enhance the gameplay experience. Enhancing the rock C-curve representation. While the rock curve is plotted correctly as a scatter plot, it might be beneficial to introduce additional visual cues or data points that help the player understand their performance better. For instance, adding tooltips or small labels that display the TPR and FPR values when hovering over the rock points could make the curve more informative. Another improvement could be to dynamically adjust the scaling of the rock canvas based on the range of TPR and FPR values generated during gameplay. This would ensure that the points are spread out more evenly across the canvas, avoiding clustering in specific areas. Improving the scoring and feedback mechanism. The scoring system currently deducts or adds points based on the player's actions, but there is an opportunity to make this feedback more immediate and engaging. For example, consider incorporating visual or auditory feedback when a player successfully identifies an abnormal waveform or makes a mistake. This could include flashing colors on the score display, playing sounds, or briefly highlighting the waveform segment that was clicked. Such feedback mechanisms can make the game more interactive and enjoyable, encouraging the player to improve their performance. Code organization and maintainability. As the game logic becomes more complex, it's important to keep the code organized and maintainable. One suggestion would be to modularize the code further by separating the waveform handling, Rossi curve plotting, and scoring logic into their own functions or classes. This would make the code easier to understand and modify in the future, especially if you plan to add more features. Additionally, consider adding comments and documentation within the code to explain the purpose of each function and variable, which will help anyone else who might work on the code in the future. Final thoughts. Overall, the code is well structured and functional, but there is room for optimization and enhancement. By focusing on improving the efficiency of waveform handling, enhancing the visual representation of the Rossi curve, refining the scoring feedback, and organizing the code for maintainability, you can create a more polished and engaging game experience. These changes will not only improve the current gameplay, but also provide a solid foundation for future development and feature additions. Enhancing the rock curve by fitting an actual line to the data points and incorporating color-coded feedback will significantly improve the visual representation and make the game more informative and engaging for the player. Let's discuss how we can implement these improvements step by step. Fitting a line to the data points. To provide a clearer visual summary of the player's performance, fitting a line to the Rossi points could be very effective. This line would represent the trend of the Rossi points and give the player an immediate sense of how their performance is evolving. One common approach to fitting a line is to use a simple linear regression, which calculates the best fit line through the scatter plot of Rossi points. This line can then be drawn on the Roxy canvas, providing a visual cue that helps the player see whether their performance is trending towards higher sensitivity and specificity. Color coding the rock points. Adding color coding to the rock points will give the player direct visual feedback on each decision they make. Correct responses can be plotted in green, indicating a positive contribution to the player's performance. Incorrect responses can be plotted in red, signaling mistakes. This immediate visual differentiation between correct and incorrect decisions will make it easier for the player to understand how each action impacts their overall performance. Adding labels to the X and Y axes. To make the rock curve more informative, it's important to label the axes. The x-axis typically represents the false positive rate, FPR, and the y-axis represents the true positive rate, TPR. Adding these labels directly to the rock canvas will help players understand what the rock curve is measuring and how their actions are reflected in the curve. Additionally, you could consider adding tick marks or grid lines for more precise reading of the rock points, although this should be done in a way that doesn't clutter the visual space. Additional enhancements. 1. Interactive feedback. Consider making the rock curve interactive. For instance, hovering over a point could display a tooltip with details such as the exact TPR and FPR values, whether the response was correct or incorrect, and perhaps even some contextual information about the specific waveform that was analyzed. This would add another layer of engagement and education for the player. 2. Dynamic scaling. If you notice that the rock points are clustering or not fully utilizing the canvas space, you might want to implement dynamic scaling. This could adjust the range of the axes dynamically based on the minimum and maximum TPR and FPR values observed so far, ensuring that the curve always occupies a significant portion of the canvas. 3. Multiple line fits. Depending on the complexity you want to introduce, you could also consider fitting multiple lines, such as separate lines for correct and incorrect responses. This could show how the player's correct and incorrect decisions trend separately over time, providing deeper insights into their gameplay patterns. 4. Customizable features. Finally, it might be worth allowing players to customize some aspects of the Rossi curve. For instance, they could choose whether to view the best fit line, toggle the visibility of incorrect responses, or adjust the sensitivity of the noise slider. These customization options could make the game more accessible and enjoyable for a wider range of players. By implementing these enhancements, you will create a more interactive and educational game that not only challenges the player, but also provides them with immediate and meaningful feedback on their performance. This will make the rock curve not just a theoretical concept, but a practical tool that players can engage with and learn from directly through gameplay. Here are more specific instructions for modifying the existing code to implement the enhancements described. 1. Fitting a line to the data points. Linear regression calculation. To fit a line through the Rossi points, you'll need to implement a simple linear regression algorithm. This will involve calculating the slope and intercept of the best fit line that minimizes the distance between the line and the Rossi points. Drawing the line. Once you have the slope and intercept, you can use the rock canvas to draw this line. It should start from the minimum x value, FPR, and extend to the maximum x value using the calculated slope to determine the corresponding y values. Color coding the rock. Assigning colors based on correctness. Modify the code that plots rock points to check whether each point represents a correct or incorrect response. If the point represents a correct identification, a hit or correct rejection, it should be plotted in green. If it represents an incorrect identification, a false alarm or miss, it should be plotted in red. Drawing points. When plotting each point on the Rossi canvas, choose the appropriate color based on the correctness of the response, and then draw the point using the existing arc function, adjusting the fill color accordingly. Have 3. Adding labels to the X and Y axes. Drawing axis labels. Add text labels to the rock canvas to indicate the axes. Label the x-axis as false positive rate FPR and the y-axis as true positive rate TPR. These labels should be placed appropriately near the edges of the canvas, with the x-axis label at the bottom center and the y-axis label rotated and placed near the left side. Optional grid lines or tick marks. If desired, you can also draw faint grid lines or tick marks along the axes to help the player better understand the scale of the rock points. These should be light in color so as not to distract from the main data points. Interactive feedback. Tooltips on hover. Implement a function that detects when the player hovers over a rock point. When this happens, display a small tooltip near the point with details such as the TPR, FPR, and whether the point represents a correct or incorrect response. This could involve adding an event listener to the rock canvas and checking the mouse position relative to the plotted points. Highlighting points. To provide more interactive feedback, you might also want to briefly highlight points when the player clicks on the waveform. For example, a point could briefly increase in size or change color when it is added to the rock curve. 5. Dynamic scaling, adjusting the axis ranges. As the game progresses, monitor the minimum and maximum TPR and FPR values. Adjust the range of the Rossi canvas axes dynamically to ensure that the points are spread out and not overly clustered. This might involve recalculating the scaling factors each time a new rock point is added and redrawing the axes with the new scale. Rescaling existing points. If the axis ranges are adjusted, ensure that all existing rock points are also rescaled and redrawn according to the new scale. 6. Customizable features. Toggle visibility of line fit and points. Add options that allow the player to toggle the visibility of the best fit line and the rock's points. This could be implemented as simple checkboxes or buttons in the game interface. When a player toggles these options, the corresponding elements on the Rossi canvas should be shown or hidden. Adjustable noise slider sensitivity. Consider allowing players to adjust the sensitivity of the noise slider itself. For example, a separate setting could allow players to choose between different noise levels or apply different noise algorithms. Code refactoring for maintainability. Modularizing the code. To keep the code organized, you should consider breaking it down into separate functions or even separate files for different tasks, such as waveform handling, rocks curve management, and scoring logic. This will make the code easier to maintain and extend in the future. Adding comments and documentation. As you implement these changes, include comments that explain the purpose of each function and the logic behind key decisions. This will help anyone who works on the code in the future understand its structure and functionality. These instructions outline the specific changes needed to implement the enhancements described earlier. Once these changes are implemented, the game will provide a more engaging and informative experience, with better visual feedback and a clearer representation of the player's performance. Following the specific instructions provided earlier, here's how you can proceed with implementing each enhancement step by step. 1. Fitting a line to the data points. Implement linear regression. The first step is to calculate the best fit line using linear regression. You'll need to sum the x and y values of the rock points, as well as their products and squares. Using these sums, calculate the slope and intercept of the line that best fits the rock points. Draw the best fit line. Once you have the slope m and intercept b, you can calculate the y value for any given x on the raw C-curve using the equation y equals mx plus b. Draw this line across the rock canvas from the leftmost to the rightmost x values, effectively summarizing the trend of the rock points. 2. Color coding the rock points. Differentiate points by correctness. As you calculate the ROS points, check whether each corresponds to a correct or incorrect response. Use this information to determine the color of the point. For correct responses, hits and correct rejections, use green. For incorrect responses, false alarms and misses, use red. Modify the drawing function. When you draw each point on the ROS canvas, set the fill style based on the correctness of the response. This will make it visually clear which points are contributing positively and which are detracting from the player's performance. 3. Adding labels to the X and Y axes. Label placement. For the X-axis label, false positive rate FPR, place the text centered along the bottom edge of the ROS canvas. For the Y-axis label, true positive rate TPR, rotate the text 90 degrees and place it along the left edge. Ensure the labels are clear but don't distract from the main content. Axis and grid lines. Optionally, you can add grid lines to help the player better interpret the rock curve. These could be faint lines or tick marks along the axes that correspond to key points such as 0.25, 0.5, and 0.75 on both the FPR and TPR scales. 4. Interactive feedback. Hover tooltips. Implement a function that tracks the mouse position on the rock canvas. If the mouse is near a rock point, display a small tooltip that shows details like the exact TPR, FPR, and whether the response was correct or incorrect. This can be done by checking the distance between the mouse position and each rock point. Highlighting on click. When a new ROSOP point is added, or when the player interacts with the waveform, briefly change the point's size or color to draw attention to it. This makes the impact of each decision immediately visible. 5. Dynamic scaling. Monitor rock ranges. Keep track of the minimum and maximum TPR and FPR values as more ROS points are added. If the points start clustering in one area of the canvas, adjust the scale of the axes to spread them out more evenly. Redraw points and axes. Whenever the axis ranges are adjusted, all ROS points and the best fit line will need to be recalculated and redrawn to match the new scale. This ensures that the ROS curve remains visually clear and informative as the game progresses. 6. Customizable features. Visibility toggles. Implement checkboxes or buttons that allow players to toggle the visibility of the ROS points and the best fit line. When toggled off, the relevant elements should be hidden from the ROS canvas. This can be done by simply skipping the drawing of these elements in the draw rock function when the corresponding toggle is off. Noise slider sensitivity. Allow players to adjust the sensitivity of the noise slider by introducing additional controls. For instance, you could add a second slider or a drop-down menu that lets players choose between different noise profiles, such as low, medium, or high sensitivity. 7. Code refactoring for maintainability. Separate functions for clarity. To make the code easier to understand and maintain, consider breaking down larger functions into smaller, more specific ones. For example, separate the logic for generating the RC curve, drawing the waveform, and handling player input into distinct functions. Modular code structure. Consider organizing the code into modules or separate files, especially if you plan to expand the game in the future. For instance, you could have one file for waveform generation, another for rock curve management, and another for UI elements like the score display and noise slider. Inline comments and documentation. As you implement these changes, make sure to add comments throughout the code. Explain the purpose of key functions, the reasoning behind complex calculations, and any non-obvious decisions you make. This will help future developers, or even yourself, understand the code more easily. By following these specific instructions, you can implement the planned enhancements in a structured and efficient manner. The result will be a more polished, informative, and engaging game that provides clear and immediate feedback to the player, making the ROC curve a central feature of the gameplay experience. Improving performance and user experience. Optimizing the game loop. Since the game loop is running frequently, ensuring that it is as efficient as possible is crucial. One way to optimize is by minimizing the number of calculations done inside the loop. For instance, pre-compute values like the noisy waveform or rock points outside of the loop, only recalculating them when necessary, e.g., when a new waveform is generated or when a new rock point is added. This can help maintain a smooth frame rate even as the game becomes more complex. Asynchronous operations. If the game is interacting with a server or performing complex calculations, such as fitting the rock curve line, ensure that these operations are done asynchronously to avoid blocking the game loop. JavaScript's async and await functions can be useful here to handle asynchronous tasks without freezing the user interface. Responsive design. Make sure the game remains playable and visually appealing across different devices and screen sizes. This can involve using CSS media queries to adjust the layout of the game elements or ensuring that the canvas and rock curve resize dynamically with the window. Testing on different devices, including mobile and tablet, will help ensure that the game is accessible to a broad audience. Enhancing visual feedback. Transitions and animations. Adding smooth transitions and animations can make the game feel more responsive and polished. For example, when the player's score changes, you could animate the score display to highlight the update. Similarly, when a new Rossi point is added, consider animating its appearance on the Rossi curve to draw attention to it. CSS animations or JavaScript-based animations can be employed here to improve the user experience. Visual indicators of game state. To help players understand their current performance at a glance, you might want to introduce visual indicators that show whether they are doing well or poorly. For instance, changing the background color of the score display to green when the player is on a good streak or red when they are making mistakes can provide immediate feedback. Similarly, you could introduce a progress bar or other visual elements that reflect the player's progress towards a high ROC score. Game over and restart mechanisms. If the game has a concept of game over, e.g., after a certain number of waveforms, ensure that this is communicated clearly to the player with appropriate visual and textual feedback. Providing a clear restart button or options to adjust settings before trying again will also improve the user experience. 10. Incorporating analytics and tracking. User performance tracking. To further enhance the educational value of the game, consider tracking the player's performance over time. This could involve saving the rocks curve data after each session and allowing the player to review their progress. By storing this data locally in the browser or on a server, you could provide insights into how the player is improving or where they might need to focus more attention. Heat maps and click tracking. Another advanced feature could be to track where players click on the waveform and use this data to generate heat maps. This could reveal patterns in the player's decision-making process, helping both the player and developers understand which waveforms are most challenging and why. Real-time data analysis. If feasible, consider integrating real-time data analysis tools that provide players with feedback on their performance trends. For example, showing a running average of the ROC score or the rate of improvement over time could make the game more engaging and informative. 11. User interface and usability enhancements. Customizable UI elements. Allow users to customize certain aspects of the game interface, such as the color scheme, font size, or the position of key elements like the score display or rock curve. This can make the game more accessible and enjoyable for a broader range of players. Error handling and user feedback. Ensure that the game handles errors gracefully, especially when interacting with external resources like servers. Provide clear feedback to the player if something goes wrong, e.g., if a server request fails or if the game cannot load. Consider implementing a fallback mechanism or offering the player options to retry or adjust settings in case of issues. Tutorials and help sections. As the game becomes more complex, players might benefit from an in-game tutorial or help section that explains how to play, what the rocks curve represents, and how their actions influence the game. This could be a simple text overlay that appears during the first few games, or a dedicated help screen accessible from the main menu. 12. Future expansion and scalability. Supporting multiple levels or difficulty modes. To keep the game engaging over time, consider introducing different levels or difficulty modes. For example, as players improve, you could introduce more complex waveforms, increase the noise level, or reduce the time available to make decisions. This keeps the challenge fresh and can help players continue to develop their skills. Modular design for easy expansion. As mentioned earlier, organizing the code into modules or separate files will make it easier to expand the game in the future. For example, if you plan to add new types of waveforms, different scoring systems, or additional gameplay features, having a well-organized code base will make these additions much simpler to implement. Community and sharing features. If the game proves popular, consider adding features that allow players to share their scores or rock curves with others. This could involve social media integration or leaderboards where players can compare their performance with others. Encouraging friendly competition or collaboration could make the game more engaging and help build a community around it. By following these more detailed instructions, you can implement the planned enhancements in a structured and efficient manner, resulting in a more polished, interactive, and scalable game. The game will not only be a fun and challenging experience for players, but also serve as a valuable educational tool that provides insights into diagnostic decision-making processes. It looks like the Rossi curve is now successfully displaying points that are color-coded based on whether the player's response was correct, green, or incorrect, red. The best fit line, which represents the overall trend of the Rossi points, is also being drawn on the canvas. This line gives a visual indication of the player's overall performance, showing how their sensitivity and specificity balance over time. However, there seems to be an issue with the waveform not being fully visible on the game canvas. It looks like the waveform might be cut off or scrolling improperly, which could be due to a mismatch in how the canvas height is being calculated or applied. This could be because the waveform is not being positioned correctly on the y-axis, causing it to appear off the visible area of the canvas. The raw C points appear to be plotted correctly, but the fact that they are clustering in a particular region could suggest that the game's scoring or rock C calculation logic might need some refinement to ensure a more even distribution of points across the rock C curve. This clustering might be due to the scoring thresholds or the way rock points are calculated based on the player's hits, misses, false alarms, and correct rejections. To address these issues, it would be helpful to 1. Re-examine how the waveform is being positioned on the
Yeah, we'll have to continue this next time. The robot is trying to improve it, so that's great. Kind of makes sense. But yeah, we have to check everything, make improvements to it. So I'll see you next time.